Picture for a moment a lone star, not drifting peacefully in the familiar disk of our galaxy, but hurtling through the vast, empty darkness of intergalactic space at a speed so unimaginable it could cross the entire span of our solar system in less than a week. This isn't a scene from science fiction. It's a real, observable cosmic event. Now, ask yourself this: what are the fastest things in existence, and how do they so completely defy our understanding of physics? We live our lives governed by a certain sense of speed, the rush of a car on a highway, the breathtaking descent of a falcon, even the incredible velocity of a spacecraft leaving our planet. But out there, in the grand theater of the cosmos, these speeds are mere standstills. The universe operates on a scale of velocity that challenges the very limits of reality itself, where objects are flung across the void by forces of almost biblical power, and where subatomic particles can be accelerated to speeds so close to the ultimate cosmic speed limit that they begin to warp the fabric of time around them. It's a realm of pure, unadulterated motion, and it holds the keys to understanding some of the deepest mysteries of existence. This video is your personal ticket on a journey to meet these speed demons of the cosmos. We are about to embark on an exploration of 30 incredible facts about the universe's fastest objects, a countdown that will take us from the colossal to the vanishingly small. We will chase after hypervelocity stars, cosmic runaways ejected from the heart of our galaxy by the monstrous black hole that resides there. We will race alongside beams of pure light and peer into the hearts of exploding stars to witness the birth of the most energetic particles known to science. This isn't just a list, it's a voyage to the very frontiers of physics, a story written in velocity and energy that reveals how our universe works in its most extreme and magnificent states. Each fact is a piece of a larger puzzle, a glimpse into the incredible forces that shape everything from the largest structures in the cosmos to the very particles that make up you and me. So get ready to have your sense of scale completely rewritten. Forget everything you thought you knew about speed and prepare to be awestruck. We're about to dive into a world where the rules are different, where distances that would take us millennia to cross are traversed in the blink of an eye, and where the concept of fast is redefined with every new discovery. This journey is designed not just to inform you, but to make you feel the sheer wonder and grandeur of a universe in constant, breathtaking motion. Let's begin our countdown and meet the champions of velocity that call this incredible cosmos home. To truly appreciate the fastest objects in the cosmos, we must first understand the ultimate rulebook of the universe, and it all begins with a single, unbreakable law. Our countdown starts not with an object, but with a fundamental constant of reality itself, the speed of light in a vacuum. This is c, a universal speed limit set at an astonishing 299,792,458 meters per second. To put that blistering pace into perspective, a beam of light could circle the entire equator of our planet not once, not 10 times, but 7.5 times in a single second. This isn't just a very high speed. It is the maximum possible speed for any form of energy, matter, or information in the cosmos. It is the universe's ultimate traffic law, and nothing with mass is ever permitted to reach this velocity. The reason for this absolute limit is deeply woven into the very fabric of space-time, as described by Einstein's theory of special relativity. As an object with mass accelerates, its energy increases. This seems straightforward, but relativity reveals a strange twist. That added energy doesn't just make the object go faster, it also makes it gain mass. It's a cosmic feedback loop. The closer you get to the speed of light, the more energy you need to accelerate further, and that very energy makes you heavier, requiring even more energy to push forward. To actually reach the speed of light, an object with any mass at all would require an infinite amount of energy, which is an obvious impossibility. This isn't an engineering challenge, it's a fundamental principle written into the blueprint of our universe. The speed of light, therefore, is not just about light itself, it is the speed of causality, the maximum rate at which any cause can produce an effect. It governs the flow of time, the behavior of particles, and the very way we perceive the cosmos. Understanding this rule transforms how we see everything else on our list. It is the gold standard, the finish line that other cosmic speedsters can only ever approach but never cross. It is the reason why the fastest massive objects we will discuss are so phenomenally fascinating. They are dancing at the very edge of what is physically possible, pushing against a boundary that the universe itself has set in stone. This ultimate speed limit ensures the stability of reality, preventing paradoxes and ensuring that the chain of cause and effect remains intact across the vast distances of space. So, as we explore the incredible velocities of stars, particles, and cosmic explosions in the facts to come, remember this foundational truth. Every other speed is measured against c, the universe's unwavering and ultimate benchmark for motion. Now that we understand the universe's ultimate speed limit, let's meet one of the most dramatic examples of an object pushing the boundaries of what's possible for something with mass. Our second fact introduces the Hypervelocity Star, a cosmic runaway flung from the heart of our own galaxy at speeds that defy belief. Imagine a star, a colossal sphere of incandescent plasma millions of times more massive than our entire planet, being ripped from its home and hurled into the infinite blackness of intergalactic space. These aren't stars peacefully drifting, they are stellar projectiles, and their origin story is tied to the most terrifying gravitational monster in our galactic neighborhood, the supermassive black hole known as Sagittarius, a star. The engine behind this incredible launch is a cosmic slingshot, a gravitational maneuver of almost perfect precision. It typically begins with a binary star system, two stars locked in a mutual dance as they orbit each other, venturing too close to the black hole's event horizon. The immense tidal forces of Sagittarius, a star, can tear this binary pair apart, capturing one star into a tight orbit around the black hole while violently flinging the other away at a phenomenal velocity. Think of it not as an explosion, but as an exquisitely powerful gravitational assist. The energy from the binary pair's orbital bond is stolen by the black hole and transferred into pure kinetic energy, catapulting the lone star outward like a stone from a sling. This process, known as the Hill's mechanism, can accelerate these stars to speeds well over 1,000 kilometers per second. At that rate, a hypervelocity star could travel the distance from Earth to the Moon in a matter of minutes. One of the most famous and fastest of these intergalactic travelers ever discovered is known as S5HVS1. Located in the constellation of Grus, this star was clocked racing away from the galactic center at a staggering 1,700 kilometers per second. That's roughly 6 million kilometers per hour. Its trajectory and speed are a perfect match for the slingshot model, pointing directly back to a close encounter with Sagittarius, a star approximately 5 million years ago. Observing stars like S5HVS1 is like finding a smoking gun at a cosmic crime scene. Their paths trace back directly to the dynamic and violent processes occurring in the chaotic core of our galaxy. The ultimate fate of these stellar exiles is as lonely as it is profound. They are moving so fast that they have achieved escape velocity from the entire gravitational pull of the Milky Way. They will never loop back, they will never settle into a new orbit. Instead, they are doomed, or perhaps freed, to travel the immense voids between galaxies. They will spend eons in utter darkness, their light a solitary beacon in an ocean of nothing, until they either fade out or, in an almost impossibly rare encounter, approach another island universe billions of years from now. These stars are more than just fast-moving objects. They are living proof of the extreme forces that sculpt galaxies, and a poignant reminder that even stars are not immune to being cast out into the cold, vast wilderness of the cosmos. But while hypervelocity stars are impressive in their linear speed across the galaxy, our next entry takes the concept of cosmic velocity and spins it into an entirely new dimension of frenzy. Fact number 3 brings us to pulsars, the spinning neutron stars that are quite literally the universe's ultimate flywheels. These objects are not just moving through space, they are rotating at speeds so dizzying that their surfaces can travel at a significant fraction of the speed of light itself. To put that into a tangible image, imagine a sphere the mass of our entire sun, compressed into a city-sized ball, and then set spinning so fast that it completes hundreds of full rotations every single second. The physics at play here are not just extreme, they are a breathtaking demonstration of one of the most fundamental laws of the cosmos. The story of a pulsar's incredible spin begins with the death of a massive star. Before it goes supernova, a typical star might be rotating quite slowly, perhaps completing one full turn over the course of several weeks or even months. But as that star's core collapses under its own gravity, something remarkable happens to its rotation. This is a consequence of the conservation of angular momentum, a principle you might have seen when a figure skater pulls their arms in during a spin and suddenly whirls much faster. In the stellar version of this, a star that was once millions of kilometers across suddenly crushes down to a diameter of only about 20 kilometers. All of the original star's rotational inertia is now concentrated into an object 100 trillion times smaller in volume. The result is a spin rate that skyrockets, transforming a languid stellar rotation into a millisecond period blur of unimaginable density. The consequences of this rapid spin are as violent as they are predictable. The centrifugal forces generated at the surface of a neutron star are so immense that they would tear any ordinary material apart instantly. Fortunately, or perhaps unfortunately, a neutron star is made of anything but ordinary material. It is a quantum object, a solid ball of neutrons packed together with a density comparable to that of an atomic nucleus. A single sugar cube-sized piece of this stuff would weigh billions of tons on Earth. It is this exotic, incredibly strong state of matter that can withstand the forces trying to fling it apart. Even so, the surface velocity is mind-bending. For a typical pulsar spinning several hundred times per second, the equator of that city-sized sphere can be moving at over 1/5 the speed of light. That means a point on its surface is tracing a circular path at tens of thousands of kilometers per second. This furious rotation is only half of what makes a pulsar a pulsar. The other half lies in its intense magnetic fields, trillions of times stronger than Earth's. These magnetic fields funnel intense beams of radiation, usually radio waves, out from the star's magnetic poles. And here's the crucial part: the magnetic axis is often tilted away from the rotational axis. So, as the neutron star spins, these lighthouse-like beams sweep through space. If one of those beams happens to cross our line of sight here on Earth, we detect a regular, repeating pulse of energy with every single rotation. This is the pulse that gives pulsars their name. The precision of these pulses is astounding. Some pulsars rival atomic clocks in their regularity, ticking with a stability that allows astronomers to use them as cosmic navigation beacons and to test the very fabric of spacetime as predicted by Einstein's general theory of relativity. They are not just dead stars, they are the universe's most accurate and energetic timepieces, born from cataclysm and spinning at the very edge of physical possibility. While pulsars demonstrate the incredible rotational speeds possible in a collapsed star, they are far from the most powerful particle accelerators in the universe. For that, we must turn our gaze to the very centers of galaxies, where a phenomenon occurs that dwarfs all others in both scale and raw power. Fact number 4 takes us into the realm of relativistic jets, colossal beams of superheated plasma that erupt from the vicinities of supermassive black holes, screaming across intergalactic space at over 99% the speed of light. These are not mere streams of gas, They are the universe's ultimate blowtorches, channeling energy on a scale that is almost incomprehensible, capable of shaping the destiny of entire galaxy clusters. The engine for this cosmic fury is what astronomers call an active galactic nucleus, or AN. At its heart lies a supermassive black hole, often weighing billions of times the mass of our Sun, and it is far from a passive vacuum cleaner. Its immense gravity pulls in vast quantities of gas, dust, and even entire stars. But this material doesn't just fall straight in. Instead, it forms a swirling, frenzied maelstrom known as an accretion disk, a structure so hot and dense that it glows with the brightness of billions of stars. Friction within this disk heats the material to temperatures of millions of degrees, turning it into a magnetized plasma, a seething soup of charged particles. It is from the inner regions of this violent whirlpool that the jets are born. The exact mechanism that launches and focuses these jets is a masterpiece of cosmic engineering, combining gravity with unimaginably powerful magnetic fields. As the black hole and its accretion disk spin, they drag the fabric of spacetime itself along with them, an effect known as frame dragging. This rotation twists the incredibly strong magnetic fields that are frozen into the plasma, winding them up into intensely coiled springs of energy. Near the black hole's poles, where the magnetic field lines are funneled together, some of the infalling material and immense amounts of energy are redirected. Instead of falling into the oblivion of the event horizon, this plasma is catapulted outward, accelerated along these magnetic highways that act like the barrel of a railgun. The acceleration is so efficient and relentless that particles are pushed to velocities indistinguishable from the speed of light itself. The result is a pair of opposing jets shooting out from the poles of the black hole system in opposite directions. Their journey does not end quickly. These jets can travel for millions, even hundreds of millions of light years, far beyond the boundaries of their host galaxy. They plow through the thin gas that exists between galaxies within a cluster, and their interaction creates gigantic, balloon-like structures known as radio lobes, which glow with synchrotron radiation. We can detect these lobes with radio telescopes, and they often dwarf the galaxy that produced them. The energy deposited into the surrounding intergalactic medium by these jets is staggering. It heats the gas, preventing it from cooling and collapsing to form new stars, effectively putting a brake on galaxy growth. In this way, the relativistic jet from a single black hole can act as a cosmic thermostat, regulating star formation across an entire cluster of galaxies for billions of years. A spectacular example of this power is the galaxy M87, home to the first black hole ever directly imaged. From its core erupts a brilliant jet of plasma that stretches for at least 5,000 light years. Observations show blobs of material within this jet moving at apparent superluminal speeds, a trick of perspective that occurs when something is moving almost directly toward us at a velocity very close to light speed. Studying such jets gives us a front-row seat to physics in its most extreme regime, where magnetic forces and gravity work in concert to create some of the most luminous and enduring structures in the entire cosmos. They are a humbling reminder that even a black hole, a symbol of ultimate consumption, can also be an engine of immense and dynamic creation, capable of projecting its influence across a significant fraction of the observable universe. And from these colossal jets that can sculpt entire galaxy clusters, we descend in scale to the very smallest and most numerous of the universe's speed demons. Fact number 5 introduces us to cosmic rays, a relentless, invisible rain of high-energy particles that constantly bombards our planet. These are not rays of light, but actual pieces of atoms, primarily bare protons, along with some atomic nuclei and electrons hurtling through the void at velocities so close to the speed of light that they carry energies defying belief. A single one of these subatomic specks can possess the kinetic energy of a professionally served tennis ball, all compressed into a particle 1 trillion times smaller than a grain of sand. They are nature's own particle accelerators, operating on a scale and with a power that makes our most impressive human-built machines, like the Large Hadron Collider, seem utterly quaint by comparison. The profound mystery surrounding cosmic rays isn't their existence but their origin. For over a century since their initial detection, scientists have been trying to pinpoint the cosmic engines capable of launching these particles to such phenomenal speeds. We know they come from somewhere beyond our solar system, and even from beyond our galaxy, but tracing them back to their source is a detective story of epic proportions. The primary reason for this challenge is that cosmic rays are charged particles, which means their paths are hopelessly scrambled by the magnetic fields that permeate interstellar and intergalactic space. A proton originating from a distant galaxy doesn't travel in a straight line to our detectors. It spirals and corkscrews along these tangled magnetic field lines, ricocheting back and forth in a chaotic journey that can last for millions of years. By the time it finally arrives at Earth, it's impossible to simply look back along its path and see where it came from. The trail has been completely erased. So, how does the universe accelerate these tiny particles to such staggering energies? The leading theory points to a process known as diffusive shock acceleration, a name that belies its incredible violence. Imagine a supernova remnant, the vast, expanding shell of debris from a stellar explosion. This shell moves through space at thousands of kilometers per second, creating a colossal shock wave, a moving wall of energized gas and magnetic fields. A proton wandering into this region can become trapped, bouncing back and forth across the shock front. With each crossing, it gains a little more speed, much like a ball being volleyed between two approaching trains. Over time, this repetitive process can boost a single proton to energies millions of times greater than anything we can create on Earth. Supernova remnants are thought to be the primary source for the majority of galactic cosmic rays, turning the death of stars into a mighty engine for particle acceleration. But the very highest energy cosmic rays, the ones that truly stretch the limits of physics, demand an even more powerful source. These ultra-high-energy cosmic rays are so rare that only a handful strike each square kilometer of our atmosphere per century, but each one carries the energy of a major league fastball. Their origins likely lie in the most cataclysmic events in the universe, the same relativistic jets from active galactic nuclei we just discussed, or perhaps the mergers of neutron stars or even more exotic phenomena. These events provide shock waves and magnetic fields on an intergalactic scale, capable of pumping particles up to energies that push the very boundaries of known physics, so high that they theoretically should interact with the cosmic microwave background radiation and lose energy over long distances, a puzzle known as the GZK cutoff. The fact that we detect them at all suggests our understanding of particle physics at these extremes is still incomplete, making each detection a potential clue to new laws of nature. This invisible rain, therefore, is more than just a curiosity. It is a continuous message from the most violent corners of the cosmos, and by catching these microscopic messengers, we are piecing together the story of the universe's greatest explosions. Yet, for all the incredible velocity of these cosmic rays and the stellar projectiles we have explored, there is a deeper, more fundamental kind of motion at work in the cosmos, one that doesn't involve objects moving through space, but rather the very fabric of space itself stretching and growing. This brings us to our sixth fact, one that redefines our understanding of speed and distance on the grandest possible scale, the expansion of the universe. We are not living in a static cosmos. We are part of a dynamic, stretching reality where the distances between galaxies are continuously increasing, not because they are flying apart through space, but because the space between them is literally being created. This isn't a force pushing things away. It is the underlying stage of the universe itself expanding, carrying the galaxies along with it like raisins in a rising loaf of raisin bread. The discovery of this monumental reality began with the work of astronomer Edwin Hubble in the 1920s. By carefully observing the light from distant galaxies, he noticed something peculiar. The light from almost every galaxy was shifted toward the red end of the spectrum. This redshift wasn't caused by the galaxies simply moving away through a static space, like a car driving away from us and its engine sound dropping in pitch. Instead, it is a direct consequence of the expansion of space itself. As light travels through the expanding cosmos, the very waves of light are stretched along with the space they are moving through, causing their wavelength to lengthen and shift toward the red. Hubble then made the critical connection. The farther away a galaxy was, the greater its redshift. This relationship is now enshrined as Hubble's law, which states that a galaxy's recession velocity is directly proportional to its distance from us. A galaxy twice as far away is receding twice as fast. This leads to a conclusion that seems to shatter everything we've just established about the cosmic speed limit. If the recession velocity increases steadily with distance, then there must be a point far enough away where galaxies are moving away from us at the speed of light. And beyond that, there are galaxies whose recession velocity exceeds the speed of light. This is not a theoretical guess. It is a direct consequence of the mathematics of an expanding universe. We have now observed galaxies so incredibly distant that the space between us and them is stretching at a rate faster than light can traverse it. This does not violate Einstein's theory of relativity, however, because relativity strictly forbids any object from moving through space faster than light. In this case, the galaxies are not themselves breaking that barrier. They are more or less stationary within their local region of space. It is the space in between that is growing, and there is no physical law that limits how fast space itself can stretch. To grasp this counterintuitive idea, imagine you are an ant standing on a perfectly elastic rubber band. You can only crawl at a maximum speed of 1 inch per second. That's your personal speed of light. Now, if someone begins stretching the rubber band, another ant further down the band will be carried away from you even if it isn't crawling at all. If the rubber band is stretched fast enough, the distance between you and the distant ant can increase at a rate of 2, 3, or even 10 inches per second. The distant ant hasn't broken any rule, it's still just sitting there. The fabric it is sitting on is what's changing. This is precisely what happens with our universe. The superluminal recession of the most distant galaxies is a global property of the expanding cosmos, not a local violation of physics. The implications of this are both profound and humbling. It means there is a cosmic horizon, a boundary beyond which we can never receive any new information. The light from galaxies receding faster than light can never reach us, as the space it must cross is expanding faster than it can travel. Those regions of the universe are forever lost to our observation, hidden behind a veil of expanding space. This also tells us that the universe is not only vast but actively becoming vaster, a dynamic reality where the very definition of distance is constantly evolving. While we chase after the fastest objects moving within space, it is the motion of space itself that ultimately governs the large-scale fate and structure of the entire cosmos, setting the stage upon which all other velocities play out. But the gravitational slingshot of a black hole is not the only way the cosmos can fling a star into the void. Sometimes the catalyst for a stellar escape comes not from an external monster, but from a violent, self-inflicted cataclysm within the star's own family. This brings us to our seventh fact, the runaway stars created by supernova explosions in binary systems. These are stellar survivors sent careening across the galaxy not by the pull of a black hole, but by the explosive death of their once close companion. The mechanism is different from the Hill's mechanism, but the outcome is similarly dramatic. A star given a sudden, violent kick that sends it on a high-velocity journey through the galaxy. To understand how this works, picture a stable binary system. Two stars orbiting a common center of gravity, bound together for millions or even billions of years. They are cosmic partners, one often more massive than the other. In the natural life cycle of stars, the more massive one burns through its nuclear fuel much faster. Its life ends not with a quiet whimper, but in a titanic supernova explosion, one of the most energetic events in the universe. In a matter of seconds, the core of this massive star collapses, triggering a shock wave that blasts the star's outer layers into space with the force of 10 octillion nuclear bombs. This sudden, asymmetric detonation is the key to the entire process. The explosion is rarely perfectly symmetrical. It might be slightly stronger in one direction, acting like a rocket engine, giving the collapsing core itself a powerful kick. But more importantly for its companion, the instant the supernova occurs, the system undergoes a radical and irreversible change. The fundamental shift is one of mass and gravity. In that single cataclysmic moment, the exploding star loses a huge portion of its mass. The remnant it leaves behind, a neutron star or a black hole, is only a fraction of the original star's weight. Since the gravitational bond holding the binary pair together was dependent on their combined mass, this sudden, dramatic weight loss shatters that bond. It's as if you were spinning a heavy weight on a string and the weight suddenly vanished, leaving you holding only the string. The surviving companion star, which was once held in a tight orbital dance, is instantly freed from its gravitational tether. The energy of its former orbit is now transformed entirely into linear motion, and it is flung away in a straight line, moving at the same velocity it had at the moment of the explosion. This is the supernova kick, a cosmic catapult that can send a star flying at speeds of several dozen to over 100 kilometers per second. A perfect and famous example of such a runaway star is Mu Columbi, a hot, brilliant blue star streaking through the constellation of Columba. Mu Columbi is an O-type star, a true stellar heavyweight, and it is moving away from a point in space in the constellation of Orion at a phenomenal velocity of over 100 kilometers per second. When astronomers traced its path backward in time, they found that its trajectory points directly back to the Orion Nebula, a vast stellar nursery about 1,300 light-years away. Even more compellingly, they discovered another runaway star, A Aurigae, also an O-type star, whose own backward traced path converges with that of Mu Columbi at the same point in Orion, and at roughly the same time in the past, about 2.5 million years ago. The evidence paints a vivid cosmic picture. It suggests that in that specific region of the Orion Nebula, there was once a tight binary system composed of two massive stars. Something caused that system to break apart violently. The most plausible scenario is that one of the two stars went supernova. The explosion was so powerful and likely asymmetric that it not only released the surviving companion, which we now call Mu Columbi, but also ejected the other massive star, A Aurigae, in the opposite direction. This three-body breakup, with the supernova remnant itself being kicked in a third direction, is a classic signature of a binary supernova disruption. Today, these two stellar siblings are hundreds of light-years apart, forever receding from the scene of their shared catastrophe. They are celestial evidence of an ancient stellar explosion, their high speed serving as a permanent record of that single, violent moment that shattered their system and sent them on solitary journeys through the galaxy. Moving from the realm of naturally occurring cosmic speedsters, we arrive at a testament to human ingenuity and our own quest to touch the sun. Fact number 8 shines a spotlight on the Parker Solar Probe, a spacecraft that officially holds the title of the fastest human-made object in history. This isn't a passive satellite drifting in Earth's orbit. It is a purpose-built marvel of engineering, a shield-bearing Voyager on a daring mission to dive repeatedly into the Sun's outer atmosphere, and in doing so, it achieves velocities that are almost incomprehensible for something we built here on Earth. At its closest approach, the probe screams through space at over 690,000 kilometers per hour. While that is still only a tiny fraction, about 0.064% of the speed of light, It is a record-breaking pace that allows it to complete a single orbit of the Sun in just 88 days, matching Mercury's year. The key to achieving such immense speed lies not in a revolutionary new engine, but in a celestial dance of orbital mechanics, specifically a series of carefully calculated gravity assists with the planet Venus. Think of it as a cosmic slingshot maneuver, a technique where a spacecraft uses the gravity of a planet to steal a tiny bit of its orbital momentum, effectively getting a powerful boost without using any fuel. The Parker Solar Probe is executing this not once, but 7 times over the course of its mission. With each close flyby of Venus, the planet's gravity pulls the probe inward, tightening its orbit around the Sun and increasing its orbital velocity. It's like a skater pulling their arms in to spin faster, but on an interplanetary scale. Each Venusian encounter acts as a brake on the probe's orbit relative to the Sun, allowing the Sun's immense gravity to pull it even closer on its next pass. This cascading effect means that with every loop, the probe's perihelion, its closest point to the Sun, gets more intimate, and its speed at that point gets more extreme. This incredible velocity is not the mission's goal in itself, but rather the necessary means to achieve its primary scientific objective, to touch the Sun, or more accurately, to plunge directly into the Sun's mysterious corona. The corona is the star's wispy, superheated outer atmosphere, visible from Earth only during a total solar eclipse as a beautiful, pearly white halo. For decades, a fundamental puzzle has baffled solar physicists. Why is the corona so unbelievably hot? The Sun's visible surface, the photosphere, is a relatively cool 6,000 degrees Celsius. Yet, just a few thousand kilometers above it, the corona rages at temperatures exceeding 1 million degrees. This is the complete opposite of what you would expect. It's as if you walked away from a campfire and suddenly felt a wave of blistering heat. The Parker Solar Probe was built to fly directly through this region and solve this mystery by taking in situ measurements of the plasma, magnetic fields, and energetic particles. To survive this hellish environment, the spacecraft is a masterpiece of thermal protection. Its most critical component is the thermal protection system, a white, lightweight shield made of a carbon composite foam that is just 4.5 inches thick. During its closest approaches, this shield faces temperatures of nearly 1,400 degrees Celsius, while the spacecraft's INSTRUMENTS Chinese letter behind it, basking in the shade at a relatively comfortable room temperature. The shield is so effective because it reflects the intense heat of the Sun rather than absorbing it, but the probe's design goes beyond just a heat shield. Its solar panels are on movable arms that can retract and extend to keep most of their surface area safely in the shadow of the heat shield, leaving only a tiny portion exposed to generate just enough power to operate. It even has a sophisticated water cooling system to circulate heat away from its sensitive electronics, a technology that one engineer described as essentially a reverse radiator. The data streaming back from the Parker Solar Probe is already revolutionizing our understanding of our home star. It has flown through the birthplace of the solar wind, the constant stream of charged particles flowing from the Sun, and observed its structure in stunning detail. It has discovered that the Sun's magnetic field near the surface is much more dynamic and switchback-like than previously predicted, with sudden, localized reversals that may be key to heating the corona and accelerating the solar wind. Every new orbit and every new data point brings us closer to answering the fundamental questions that drove this mission. The Parker Solar Probe stands as a stunning achievement, a symbol of our species' relentless curiosity. It is a human-built object forged on our small world that is now dancing with planets and diving into a star, not just as the fastest thing we have ever created, but as our most intimate window into the heart of our solar system. After witnessing the raw power of a supernova kicking a star across the galaxy, we now turn to a phenomenon that is not an object moving through space, but a literal vibration of space itself. Our ninth fact brings us to gravitational waves, the ripples in the very fabric of space-time that travel at the ultimate cosmic speed, the speed of light. For centuries, we have studied the universe by observing light, from the visible colors to radio waves and X-rays. But gravitational waves are an entirely different kind of messenger. They allow us to hear the cosmos, to perceive the vibrations generated by its most violent and energetic events, opening a window onto a universe that was previously completely dark to us. The story of these waves begins with Albert Einstein and his theory of general relativity, published in 1915. Einstein proposed that what we perceive as gravity is not a mysterious force pulling objects together, but rather the curvature of space-time caused by mass and energy. Imagine space-time as a vast, taut, elastic trampoline sheet. Place a heavy bowling ball in the center, and it creates a deep depression. A nearby marble will roll toward the bowling ball, not because of a force, but because it is following the curved geometry of the trampoline fabric. Now, imagine what happens if you rapidly wobble that bowling ball back and forth. It would send ripples moving outward across the trampoline surface, waves of compression and stretching in the fabric itself. This is the essence of a gravitational wave. They are not waves in space, they are waves of space, rhythmic distortions that alternately squeeze and stretch the distance between objects as they pass by. Einstein himself was convinced these waves would be so incredibly faint that they would never, ever be detected. He was right about their weakness. The ripples from even the most cataclysmic events in the universe cause distortions on Earth thousands of times smaller than the nucleus of an atom. The key to detecting them lay in finding events of almost unimaginable violence, where colossal masses are accelerated to a significant fraction of the speed of light. The perfect source is the merger of two black holes. As these unimaginably dense objects spiral inward toward their final collision, they whip around each other hundreds of times per second, churning the space-time around them like a cosmic blender. This motion generates an intense, spiraling burst of gravitational waves that carries away phenomenal amounts of energy, propagating outward at the speed of light in all directions. This is the cosmic drumbeat that, after a journey of 1 billion years, we finally learned to hear. The instrument that made this historic first detection possible is the Laser Interferometer Gravitational Wave Observatory, or LIGO. It is not a traditional telescope that collects light, but a colossal listening device. LIGO consists of two identical facilities in the United States, separated by nearly 2,000 miles to rule out local false signals like a passing truck. Each facility is built in the shape of an immense L with two arms, each exactly 4 kilometers long. Inside these vacuum pipes, a powerful laser beam is split in two, with each beam traveling down an arm and reflecting off a mirror suspended at the end. In normal circumstances, the two beams travel the exact same distance and return to cancel each other out. But when a gravitational wave passes through the Earth, it minutely changes the length of the arms. One arm gets imperceptibly shorter while the other gets longer, and then they switch. This tiny change, smaller than 1/10,000th the width of a proton, is enough to disrupt the laser beam's perfect cancellation, allowing a flicker of light to reach the detector. The genius of LIGO is its ability to measure this infinitesimal fluctuation. The first direct observation, announced in 2016, was a moment that shook the scientific world. On September 14, 2015, both LIGO detectors in Louisiana and Washington state recorded an identical signal. The data was transformed into an audible sound, a distinctive chirp that started at a low frequency and rapidly swept upward in pitch before ending abruptly. This was the fingerprint of two black holes, one about 36 times the mass of the Sun and the other 29. Completing their final, fatal orbits and merging into a single, more massive black hole about 62 solar masses. In the final fraction of a second of their merger, they radiated away 3 whole solar masses worth of pure energy in the form of gravitational waves. a power output greater than all the stars in the observable universe combined. That chirp was the sound of that energy ringing across the cosmos, a direct confirmation of a 100-year-old prediction and the dawn of an entirely new field of astronomy. Since that first historic detection, the collaborative network of observatories, including Europe's Virgo detector, has heard the cosmic drumbeats of many more events. We have listened to the mergers of neutron stars, collisions that not only send out gravitational waves, but also a brilliant flash of light across the electromagnetic spectrum, allowing us to witness the creation of heavy elements like gold and platinum. Each new detection adds a new data point, a new sound to our growing symphony of the violent universe. Gravitational wave astronomy has given us a direct line to the most energetic processes in existence, allowing us to test general relativity in the most extreme gravitational fields and to census the population of black holes that would otherwise be completely invisible. We are no longer just stargazers, we have become cosmic listeners, our ears pressed to the fabric of space-time, hearing the echoes of collisions that happened long before our planet was even born. After listening to the cosmic drumbeats of colliding black holes, we now turn our attention to a different kind of signal, one that arrives not as a low-frequency chirp, but as a brilliant, fleeting scream across the radio spectrum. Fact number 10 catapults us into the mystery of fast radio bursts, or FRB. These are not gentle waves, they are the universe's most powerful and enigmatic firecrackers, intense flashes of radio waves that last for just a few thousandths of a second, yet in that blink of an eye, they release more energy than our sun puts out over 80 years. What makes them truly staggering is their journey. They travel across billions of light-years of intergalactic space, enduring a cosmic obstacle course of diffuse gas and magnetic fields, only to finally be captured by our telescopes as a sharp, unmistakable spike on a graph. They are both a profound puzzle and a potential new tool for probing the vast, empty spaces between galaxies. The story of their discovery is a modern tale of serendipity and data mining. It was 2007 when astronomer Duncan Lorimer and his student David Narkevic were poring over archival data from the Parkes Radio Telescope in Australia, recorded 6 years earlier. They were looking for something else entirely when they found it, a single colossal burst of radio energy that lasted a mere 5 milliseconds. It was so bright and so brief that for a time, many in the scientific community were skeptical, suggesting it might be a local glitch, perhaps from an errant microwave oven on the observatory grounds. But then, other telescopes started finding them too. As more of these bursts were detected, it became undeniable that they were real and that they were coming from deep space. Their extreme dispersion, a telltale smearing of the signal caused by electrons in intergalactic space, confirmed their cosmological origins. They weren't from our galaxy, they were messengers from halfway across the observable universe. The central, thrilling mystery of fast radio bursts is, of course, what creates them. The list of potential culprits reads like a roster of the most extreme objects we've already discussed, pushed to their absolute limits. One of the most promising suspects is the magnetar, a type of neutron star we met earlier, but with a terrifying upgrade. A magnetar is a neutron star with a magnetic field so immensely powerful it defies comprehension, 1,000 trillion times stronger than Earth. These fields are under unimaginable strain, and they can suddenly crack the star's rigid crust in what's known as a starquake. This seismic event on a stellar scale releases a titanic amount of magnetic energy, which theorists suggest could be funneled into an incredibly focused beam of radio waves, a fast radio burst. In 2020, we caught one in the act. Observations confirmed that a known magnetar within our own Milky Way galaxy produced a radio burst that, while much weaker than the extragalactic ones, had all the same characteristics. This was a smoking gun, proving that at least some FRBs are born from these magnetic monsters. Yet, magnetars may not be the only source. the incredible power of the most distant bursts suggests other cataclysmic origins are also at play. Another compelling theory points to the merger of two neutron stars, the same kind of event that produces gravitational waves and showers of gold. As two such ultra-dense objects spiral together, their immense magnetic fields could become tangled and reconfigure in a colossal short circuit, releasing a torrent of radio energy in a final, brilliant flash. There are even more exotic possibilities, such as the evaporating black holes predicted by some theoretical models, or the eruptions from intensely active galactic nuclei. And then there is the most speculative but endlessly fascinating idea: could they be artificial? Could they be the lighthouse signals of an advanced interstellar civilization? While this is considered highly unlikely by most scientists, the sheer unexplained power and brevity of these signals force us to keep all possibilities, however remote, on the table until the evidence definitively rules them out. What makes FRBs more than just a cosmic curiosity is their potential use as tools for fundamental science. Because these radio waves have to travel through the sparse plasma that exists between galaxies, they get delayed by the free electrons they encounter. The higher frequency parts of the burst arrive slightly before the lower frequencies, and this delay, this dispersion, is a direct measure of how much material the signal has passed through. By measuring the dispersion of a single FRB, astronomers can effectively count the total number of electrons along its line of sight. This allows them to weigh the missing ordinary matter in the universe, the so-called missing baryon problem, where a vast amount of matter that theories predict should exist had simply not been found. FRBs are now acting as cosmic dipsticks, confirming that this missing matter is indeed there, floating in a diffuse, hot gas in the intergalactic medium. They are illuminating the darkness between the galaxies in a way no other tool can. Adding another layer of complexity to the mystery, we have discovered that not all fast radio bursts are one-off events. Some sources are repeaters, firing off multiple bursts from the same location in the sky, but with no predictable pattern. This repetition immediately rules out one-time cataclysmic events like a neutron star merger for those specific sources. It strongly points to an object that can survive its own outburst, like a magnetar that can have multiple starquakes. The contrast between the one-off bursts and the repeating bursts suggests we are likely dealing with at least two different populations, perhaps even two or more distinct physical mechanisms. Every new detection, especially from powerful new telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, which is discovering them by the dozens, adds another piece to this intricate cosmic puzzle. Fast radio bursts represent a frontier of astronomy where the questions still far outnumber the answers, a thrilling reminder that the universe is still full of brilliant, fleeting signals waiting for us to decipher their origin and unlock the secrets they carry across the cosmos. But even the immense gravity of a supermassive black hole or the explosive kick of a supernova cannot fully explain the motions we see on the very largest scales. Our journey now takes us beyond individual objects to the grand architecture of galaxies themselves, where we encounter one of the most profound and persistent mysteries in all of modern cosmology. Fact 11 brings us to the beautiful Whirlpool Galaxy, a classic spiral spinning in space, and a cosmic puzzle that provided some of the most compelling early evidence for the existence of dark matter. The clue was not found in the bright, central core, but in the behavior of stars and gas in the galaxy's faint, distant outskirts, moving at speeds that should have been physically impossible. The puzzle, known as the galaxy rotation problem, is a classic case of expectation versus reality. According to the well-understood laws of gravity, a spiral galaxy should behave much like our own solar system. The Sun, containing over 99% of the solar system's mass, sits at the center. The planets orbit around it, and their speeds are dictated by this central mass. Mercury, the innermost planet, moves very fast, while the outer planets like Neptune and Pluto move much more slowly. For decades, astronomers assumed that the visible mass of a galaxy, its central bulge of stars and its bright spiral arms, was also concentrated toward the center. They logically expected that stars orbiting far out in the galactic suburbs, in the dim, sparse regions, would therefore be moving at relatively sedate, leisurely paces. When astronomers began to carefully measure the orbital velocities of stars and hydrogen gas clouds at different distances from the centers of spiral galaxies like the whirlpool, they received a profound shock. The data revealed a flat rotation curve. This means that instead of the predicted dramatic drop-off in speed as you move further from the center, the orbital velocities remained stubbornly high, all the way out to the very edges of the observable galaxy. A star 60,000 light-years from the core was moving just as fast as a star only 20,000 light-years out. This was as if Pluto were orbiting the Sun at the same breakneck speed as Mercury, a clear and direct violation of the predictions made by the gravity of the visible matter alone. There was only one plausible conclusion. There had to be a tremendous amount of unseen mass, a form of matter that does not emit or interact with light, providing the extra gravitational glue to hold these swiftly moving outer stars in their orbits. This invisible mass is what we now call the dark matter halo. Imagine the beautiful, luminous spiral disk of the whirlpool galaxy that we see in photographs is just the bright, shiny jewel at the center of a colossal, invisible sphere. This sphere, the halo, is vastly larger than the visible galaxy and contains over 90% of the galaxy's total mass. It is this immense, unseen gravitational anchor that dictates the motion of the outer stars. Their unexpectedly high speeds are not a fluke, they are a direct measurement of the dark matter's pull. The visible galaxy is essentially just floating within this much larger and more massive cloud of dark matter, which itself remains completely transparent and undetectable by any telescope that relies on light from radio waves to gamma rays. The evidence from the Whirlpool Galaxy and countless others since has forced a fundamental rewrite of our understanding of the cosmos. We now realize that the glittering stars and glowing gas clouds that make up the familiar sky are merely the visible tracers, the froth on the surface of a deep, dark ocean. The true cosmic landscape is dominated by this mysterious substance that outweighs ordinary matter by a factor of 5 to 1. It is the dark matter that provides the scaffolding upon which galaxies form and the gravitational potential wells that hold them together, preventing them from flying apart due to the rapid rotation we observe. Without this hidden framework, galaxies as we know them simply could not exist. The outer stars would have been flung off into intergalactic space long ago. The high-speed dance of the stars on the outskirts of the Whirlpool Galaxy is therefore one of the most important clues we have, a silent testimony to the pervasive presence of the universe's greatest unseen component. And from the grand, dark halos that bind entire galaxies, we now turn our attention to a much smaller, but no less significant traveler, one that visited our own cosmic backyard. Fact 12 introduces us to Oumuamua, the first confirmed interstellar object ever detected passing through our solar system. In October 2017, astronomers at the University of Hawaii's Pan-STARRS 1 telescope spotted a faint point of light moving against the backdrop of stars. It was immediately clear this was no ordinary asteroid or comet from our own system. Its incredible speed and its path were unlike anything ever seen before. This visitor was moving too fast to be bound by the sun's gravity, and it was already on its way out, a fleeting guest that had already made its closest approach to the sun and was now racing back into the depths of interstellar space. The object was given the name Oumuamua, a Hawaiian word that aptly means a messenger from afar arriving first. Its velocity relative to the sun was a blistering 26 kilometers per second as it departed, a speed that definitively placed it on a hyperbolic trajectory. Unlike the closed, elliptical orbits of comets and asteroids that belong to our solar system, A hyperbolic orbit is an open curve, like a slingshot path that never returns. This was the ultimate proof that Oumuamua was not from here. It was a piece of another star system, a cosmic wanderer that had been traveling for millions, perhaps even billions, of years before its chance encounter with ours. Its very existence confirmed a long-held theory that planetary systems routinely eject trillions of small bodies into the galactic void, and we had finally caught one in the act. But the simple fact of its origin was where the simplicity ended, because Oumuamua was profoundly strange. The first major puzzle was its shape. By carefully analyzing how its brightness changed over time, astronomers determined that it was not a roughly spherical object. Instead, it was tumbling end over end, and the dramatic variations in its light curve suggested an extremely elongated, cigar-like shape, with estimates suggesting it was up to 10 times longer than it was wide. Nothing like this had ever been observed in our solar system, where such extreme ratios are unheard of. This bizarre geometry immediately sparked intense debate. How could such a fragile shape survive the rigors of interstellar travel, with its constant bombardment by cosmic rays and tiny dust grains? Was it a shard from a planetary collision, a unique product of its home system's formation? The second major surprise was what happened as it passed the Sun. Most comets, when they approach the Sun, heat up and develop a distinct coma, a fuzzy envelope of gas and dust, and often a tail. Oumuamua showed no visible coma or tail whatsoever, appearing completely asteroidal in our observations. Yet, when astronomers precisely tracked its path, they found it was experiencing a tiny but persistent non-gravitational acceleration. It was moving slightly differently than what could be explained by the gravity of the Sun and planets alone. For comets, this kind of acceleration is common and is caused by outgassing, the jet-like effect of ices turning to gas and streaming off the surface. But if Oumuamua was outgassing, why was there no coma, no dust, no visible evidence? This was the central paradox. It was moving like a comet but looked like an asteroid. This mystery led to a fascinating spectrum of proposed explanations, ranging from the conventional to the highly speculative. One compelling natural explanation is that Oumuamua could have been a fractal-like aggregate of dust, a so-called dust bunny with a very low density and a high surface area. This could explain the non-gravitational acceleration through the sublimation of water ice deep within its porous structure, with the gas escaping through pores too small to drag any visible dust particles with it. Another possibility is that it was a shard of a Pluto-like planet that was torn apart by its home star, a chunk of nitrogen ice that would sublimate and cause acceleration without producing a dusty coma. Then, of course, there was the more sensational, though far less likely, hypothesis proposed by Harvard astronomer Avi Loeb, that it could be a piece of alien technology, perhaps a light sail from a distant civilization. While the scientific consensus strongly favors a natural origin, the very fact that such an idea was seriously discussed highlights just how peculiar and anomalous this object truly was. The legacy of Oumuamua is immense. It taught us that interstellar objects are not just theoretical, they are real and passing through our solar system with some frequency. It forced astronomers to create a new classification category for such visitors and has spurred plans for future missions, like the European Space Agency's Comet Interceptor, which is designed to lie in wait for the next such interstellar object, ready to launch and rendezvous with it. Oumuamua was a one-of-a-kind discovery, a tiny, enigmatic rock that challenged our definitions and our understanding of what is possible. It was a literal piece of another star system, a postcard from a place we will never see, and its brief, puzzling passage through our neighborhood has forever changed our perspective, reminding us that the galaxy is not just a collection of distant stars, but a dynamic environment teeming with fast-moving, silent travelers. Yet, for all the astounding velocities we have catalogued, from hypervelocity stars to beams of plasma, every single one still obeys the universe's ultimate traffic law, traveling at or below the speed of light. But what if we could break that rule? What if there were entities for which the light speed barrier was not a ceiling but a floor? This brings us to our 13th fact, a journey into the realm of pure theory and one of the most mind-bending concepts in physics, tachyons. These are hypothetical particles that, by their very nature, would always travel faster than light. They are not just fast, they are fundamentally superluminal, inhabiting a strange and paradoxical domain of reality that, if it exists, would force us to rewrite our understanding of cause and effect. The theoretical foundation for tachyons emerges from the mathematics of Einstein's special relativity itself. The famous equation E equals mc squared has a more general form that relates an object's energy, momentum, and mass. For all ordinary particles with real, positive mass, this equation forces them to travel slower than light. But mathematicians noticed that if you plug in a value for an object's velocity that is greater than the speed of light, the equation suggests its mass would have to become an imaginary number. This isn't a number in the everyday sense. It's a mathematical concept involving the square root of -1. Rather than dismissing this as nonsense, some physicists wondered if it could describe a new class of particles, tachyons, from the Greek word tachys, meaning swift, that are born faster than light and can never slow down to the speed of light or below. Their imaginary mass is not a physical substance with weird properties, but a mathematical placeholder indicating their inherently superluminal nature. The real Pandora's box that tachyons open, however, is not about mass, but about causality, the fundamental principle that cause must always precede effect. According to the rules of relativity, if information could be transmitted faster than light, it would lead to scenarios where an observer in one frame of reference could see an effect happen before its cause. Imagine you could send a tachyon message to your own past. You might send a signal that tells your past self not to send the message in the first place. This creates a logical paradox, a loop where the message both is and isn't sent, undermining the consistent flow of time. For most physicists, this is the most powerful argument against the existence of tachyons. They seem to allow for the possibility of time travel and violate causality, leading to universe-breaking contradictions that most physical laws are built to avoid. This has not stopped scientists from looking for them. If tachyons did exist, how might we detect them? One proposed method involves a phenomenon similar to Cherenkov radiation. When a charged particle like an electron travels through water faster than the speed of light in that medium, it produces a characteristic blue glow. By analogy, a superluminal tachyon moving through a vacuum, which has a higher speed of light than light itself in a medium, might produce a unique type of radiation as it slows down. Though in the tachyon's case, slowing down means approaching the infinite energy barrier at the speed of light from above. Experiments have searched for this telltale signature, and others have looked for anomalous energy losses in particle collisions that could be explained by the creation of tachyons, but no credible evidence has ever been found. Their continued absence from our detectors strongly suggests that if they are real, they do not interact with ordinary matter in any way we can perceive, making them effectively ghosts in the cosmic machine. The enduring legacy of the tachyon, therefore, is not as a discovered particle, but as a powerful thought experiment. It serves as a critical stress test for the foundations of modern physics, forcing us to confront the deep connection between faster-than-light travel and the logical flow of time. It highlights the robustness of special relativity, showing that its prohibition on superluminal matter is not an arbitrary rule, but one that protects the very consistency of reality. While they remain a fascinating staple of science fiction in the world of theoretical physics, tachyons are a brilliant specter, a concept that teaches us more about the rules of our universe by showing us what might be possible, or more importantly, what must be forbidden, in order for our cosmos to function as a coherent and predictable whole. While we have been chasing the fastest individual objects, it's easy to forget that we ourselves are on an incredible high-speed journey. Fact 14 brings this cosmic velocity home, revealing that our entire solar system is locked in a breathtaking orbital dance around the center of the Milky Way galaxy. We are all moving at approximately 230 kilometers every second, a pace that would take us from Earth to the Moon in less than half an hour. This isn't a gentle drift, it is a continuous, sweeping arc around a gravitational center 26,000 light-years away, a journey so vast that a single complete orbit, one galactic year, takes our solar system roughly 230 million years to finish. To truly appreciate the scale of this motion, consider the last time our planet was in this same position within the galaxy. It was the late Triassic period. The supercontinent of Pangaea was just beginning to rift apart, and the very first dinosaurs were emerging to walk the Earth. In the 230 million years it has taken for us to complete just one lap, dinosaurs rose, dominated, and vanished. Mammals evolved from tiny shrew-like creatures into the incredible diversity of life we see today, including ourselves. All of recorded human history, from the first cities to the modern digital age, occupies less than the final blink of an eye in this single galactic year. This timescale redefines our place in the cosmos. We are transient passengers on a celestial carousel of almost unimaginable slowness and grandeur. So, what provides the immense gravitational pull to keep our Sun and billions of other stars whipping around at such high velocities? The force does not come from a single point, but from the combined gravitational influence of everything inside our solar system's orbit. The most significant visible component is the galaxy's central bulge, a dense, spherical swarm of primarily older, redder stars that packs a tremendous amount of mass into a relatively small volume. However, as we learned from the Whirlpool Galaxy, the visible matter alone is not nearly enough to account for the observed orbital speeds. The true powerhouse of the galaxy's gravity is its immense spherical halo of dark matter. This invisible framework, which extends far beyond the visible disk of the Milky Way, provides the dominant gravitational anchor. It is the combined pull from this central bulge of stars and this vast, unseen dark matter halo that creates the deep gravitational well we are orbiting, ensuring our solar system doesn't fly off into the intergalactic void. This galactic rotation also provides profound context for the other high-speed objects we have discussed. When we observe a hypervelocity star racing away from the galactic center at 1,700 kilometers per second, that velocity is measured relative to that central rest frame. That star isn't just moving fast on its own, it is moving fast relative to us, who are already hurtling along at 230 kilometers per second in our own galactic orbit. Our motion is the background against which we measure these cosmic projectiles, a constant high-speed cruise that forms the baseline for all other velocities within our galaxy. It is a humbling and dynamic reminder that there is no such thing as a truly stationary point in the universe. We are all, from the smallest asteroid to the largest star, participants in a grand, complex, and never-ending gravitational dance. But to truly witness a relativistic jet in its most extreme and furious form, we need to look at a very specific and special kind of cosmic monster. This brings us to fact 15. Blazars, the supercharged, beamed headlights of the universe. Imagine you are standing in a dark field and someone points a brilliant spotlight directly into your eyes. The light appears overwhelmingly bright, drowning out everything else, and if the person holding the spotlight were to flicker it on and off, that flickering would be all you could see. Now replace that spotlight with a relativistic jet of plasma, screaming from the poles of a supermassive black hole at over 99% the speed of light, and point that jet directly at our line of sight here on Earth. What you get is a blazar, one of the most luminous and violently variable objects in the entire cosmos. The engine of a blazar is fundamentally the same as that of any other active galactic nucleus. a supermassive black hole weighing millions to billions of times the mass of our Sun, greedily feeding on a swirling accretion disk of superheated gas. The difference lies entirely in our perspective. For a blazar, we are looking almost directly down the barrel of one of its jets. This special alignment has a profound and dramatic effect on the light and radiation we receive, due to a phenomenon predicted by Einstein's special relativity known as relativistic beaming. Because the material in the jet is moving toward us at a velocity indistinguishable from the speed of light, the light it emits gets squashed together, its waves compressed. This dramatically boosts its brightness and shifts its frequency higher. It's like the Doppler effect for a siren, but for light, and amplified to an almost unimaginable degree. The jet pointed at us can appear hundreds or even thousands of times brighter than the jet pointing away, making the entire galaxy's core look like a single, brilliant point of light. The consequences of this alignment are spectacular. A blazar doesn't just shine steadily, it is a cosmic strobe light capable of doubling its brightness in a matter of hours or even minutes. This incredible variability is a direct window into the chaotic processes happening on extremely small scales near the black hole's event horizon. A flare in brightness could correspond to a sudden clump of matter falling in, a reconnection of magnetic field lines, or the ejection of a new, particularly energetic blob of plasma from the very base of the jet. Because the jet is pointing right at us, we can observe these tiny, rapid fluctuations that would be completely washed out if we were viewing the system from the side. This makes blazars unparalleled natural laboratories for studying black hole physics in real time. The energy output of a blazar is staggering, and it doesn't just come in one form of light. They are true multi-wavelength powerhouses, emitting intense radiation across the entire electromagnetic spectrum, from low-energy radio waves through visible light up to incredibly energetic X-rays and gamma rays. In fact, some of the most powerful steady sources of gamma rays in the sky are blazars. This gamma-ray emission is particularly telling, as it is generated by the most energetic particles within the jet. These particles, likely electrons and protons accelerated to near light speed by shock waves within the jet, collide with lower-energy photons, boosting them up to gamma-ray energies in a process known as inverse Compton scattering. When a blazar enters a flaring state, its gamma-ray output can completely dominate the entire high-energy sky, outshining every other source for a brief, brilliant period. One of the most famous and well-studied blazars is known as Markarian 421. Located about 400 million light-years away, it has been a subject of intense observation for decades, serving as a prototype for understanding the entire class. Its brightness fluctuates wildly across all wavelengths, and it has been caught in some of the most extreme outbursts ever recorded. By coordinating observations from radio telescopes on the ground to gamma-ray satellites in space, astronomers can piece together a timeline of an eruption as it travels along the jet, helping them understand how these cosmic particle accelerators work. Studying blazars like Markarian 421 is crucial because their beams carry information from the deepest gravitational wells in the universe, allowing us to probe physics under conditions that are forever impossible to recreate in a laboratory on Earth. They are the universe's most powerful and persistent signal, a targeted scream of energy that, by a fortunate cosmic alignment, shines directly upon us, revealing the furious heart of a distant galaxy. While we look across the universe for incredible speeds, one of the most powerful particle accelerators is located right in our own solar backyard, and its eruptions can directly reach out and touch our modern world. Fact 16 brings us to the explosive fury of our own sun, focusing on solar flares and coronal mass ejections. These are not gentle events. They are the star's most violent tantrums, capable of hurling billions of tons of superheated solar plasma into space at speeds that can exceed 3,000 kilometers per second. To put that into perspective, that's fast enough to travel from the Earth to the Moon in just over 2 minutes. This isn't a steady wind, it is a solar hurricane, and its origin lies in the incredibly complex and strained magnetic fields that writhe across the Sun's surface. The key to understanding these explosions is a process known as magnetic reconnection. Think of the Sun's surface not as a calm, smooth ball of fire, but as a seething cauldron of magnetism. Intense magnetic fields are generated by the churning plasma in the Sun's interior, and they often arc up through the surface in vast loops, channeling and containing the million-degree gas of the corona. Sometimes these field lines become twisted, strained, and tangled, storing immense energy like a coiled spring. Magnetic reconnection is the moment that spring suddenly snaps into a new, lower-energy configuration. It occurs when oppositely directed magnetic field lines are forced together, break, and then reconnect in a different arrangement. This sudden reconfiguration releases a colossal amount of stored magnetic energy all at once, an amount equivalent to millions of hydrogen bombs detonating simultaneously. This released energy does two primary things. It violently heats the local plasma to tens of millions of degrees in a brilliant flash of radiation we call a solar flare, and it can simultaneously blast a massive bubble of plasma and magnetic field clear off the Sun in a coronal mass ejection. It's crucial to distinguish between these two related but distinct phenomena. A solar flare is the intense flash of light, a burst of radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. It is the electromagnetic signature of the magnetic explosion, and its light reaches Earth in just over 8 minutes. A coronal mass ejection, or CME, on the other hand, is a physical thing, a colossal cloud of magnetized plasma, often containing billions of tons of solar material that is ejected from the Sun's atmosphere. While flares and CMEs often occur together, they don't always. A CME is the slower, more massive, and ultimately more geopolitically significant event. It can take anywhere from half a day to 3 days to travel the 150 million kilometers to Earth, but when it arrives, it carries the potential to fundamentally disrupt the technological infrastructure our society depends on. The impact of a direct hit from a powerful coronal mass ejection is a stark reminder that we live in the atmosphere of a dynamic star. When this giant cloud of magnetized plasma collides with Earth's own magnetic field, it compresses it and transfers energy into our planet's magnetosphere. This can trigger a severe geomagnetic storm, one of the most spectacular manifestations of which is the aurora, pushing the northern and southern lights to much lower latitudes than normal. But the beautiful lights are merely the visible side of a much more dangerous phenomenon. The rapidly shifting magnetic fields induce powerful electrical currents in the ground and in any long conductor, most notably in our continental-scale power grids. These geomagnetically induced currents can overload transformers, the massive and difficult-to-replace hearts of our electrical systems, causing them to heat up, fail, and even burn out. The benchmark for this kind of disaster is the Carrington event of 1859, named after the astronomer who observed the colossal solar flare that preceded it. The ensuing coronal mass ejection was so powerful that it caused telegraph systems, the high-tech communication network of the era, to fail worldwide. Operators received shocks, telegraph paper caught fire, and some lines operated on the induced currents alone, even with their power supplies disconnected. If an event of that magnitude were to occur today, the consequences would be catastrophic on a global scale. It could cause widespread, long-lasting power outages lasting for months, crippling water supplies, refrigeration, fuel distribution, and financial systems. The total economic impact is estimated to be in the trillions of dollars. This is not mere speculation. A powerful CME narrowly missed Earth in 2012, and scientists confirmed it was of a similar magnitude to the Carrington event. We got a free pass that time, but it underscored the very real and present danger. Because of this threat, a global network of ground-based and space-based observatories constantly monitors the Sun. Satellites like NASA's Solar Dynamics Observatory provide stunning high-resolution images of the solar surface, while the Solar and Heliospheric Observatory and the Deep Space Climate Observatory give us crucial advance warning of Earth-directed coronal mass ejections. This early warning, even if only a matter of hours, allows power grid operators to take defensive measures, such as bringing additional generation capacity online and temporarily putting systems into a safe configuration to mitigate the worst effects of the induced currents. Studying these solar explosions is not just an academic pursuit, it is a critical part of planetary defense. By understanding the magnetic reconnection process that drives them, we improve our space weather forecasting, giving our technologically fragile civilization the precious time it needs to batten down the hatches before the next great solar storm arrives. Yet, even as we race around the galactic center at hundreds of kilometers per second, that motion is itself just a small component of a much larger, more powerful flow. Our 17th fact pulls back the camera to the scale of the entire observable universe, where we encounter the Great Attractor, a mysterious and colossal gravitational anomaly that is pulling our entire Milky Way galaxy, along with thousands of others, toward it at an incredible 600 kilometers per second. This isn't just our local orbit, this is our entire galactic neighborhood being dragged through the cosmos like a leaf caught in a vast, invisible river. The story of its discovery is a classic scientific detective story, one that began with meticulous observations of how galaxies move against the grand backdrop of the expanding universe. In the 1970s and 80s, astronomers were busy mapping the large-scale structure of the cosmos by measuring the redshifts of thousands of galaxies. They expected to see a clean, uniform expansion in all directions, a perfect Hubble flow where every galaxy recedes from every other galaxy. But when they looked at the motions of galaxies in our own celestial vicinity, including the Milky Way, they found a significant deviation. Our local group of galaxies, along with the entire Virgo cluster and thousands of other systems, all showed a peculiar velocity, a shared motion on top of the general expansion, streaming toward a specific patch of the sky in the constellation of Centaurus. This collective drift became known as the dark flow, and the unseen source of this immense gravitational pull was dubbed the Great Attractor. It was as if we had discovered a colossal waterfall in space, with our galaxy floating helplessly toward the precipice. The initial challenge in solving this mystery was a frustrating one. The direction of the Great Attractor lies directly behind the plane of our own Milky Way galaxy, a region astronomers call the zone of avoidance. This band of the sky is flooded with the light, gas, and dust of our own galactic disk, which obscures our optical view of the distant universe beyond, much like trying to see a distant mountain range through a thick ground-level fog. For decades, the heart of the Great Attractor was hidden behind this cosmic veil, leaving scientists to speculate about what kind of structure could possibly wield such gravitational influence. Early estimates suggested it would need to be a concentration of mass tens of thousands of times more massive than our entire Milky Way, a truly monstrous overdensity in the cosmic web. The breakthrough came with the ability to peer through the zone of avoidance using wavelengths of light that can penetrate interstellar dust, primarily infrared and radio surveys. Pioneering work using radio telescopes to map the distribution of hydrogen gas revealed that there were indeed thousands of galaxies hidden behind our own disk. This began to paint a clearer picture of the attractor, but the true cosmic revelation arrived with the detailed study of galaxy motions on an even grander scale. In 2014, a team of astronomers announced the definition of a new supercluster of galaxies, an immense structure they named Laniakea, which means immense heaven in Hawaiian. Our Milky Way, it turns out, is not just a member of the Virgo supercluster, but a tiny outpost on the far-flung fringe of the much vaster Laniakea supercluster. Laniakea is a filamentary web of roughly 100,000 galaxies, stretching over 500 million light-years across. The Great Attractor is not a single, mysterious object, but rather the gravitational center of mass for this entire supercluster. It acts as the central basin, the focal point toward which all the galaxies within Laniakea are gradually flowing. The 600 km/s motion of our galaxy is simply our participation in this immense gravitational tide, our long-term trajectory toward the densest knot in our local cosmic neighborhood. The Great Attractor itself is now understood to be the core of the Norma cluster, a massive gathering of galaxies located about 250 million light-years away, whose combined gravity, amplified by the surrounding dark matter halo of Laniakea, creates the pull we feel. This discovery fundamentally reshapes our cosmic address. We are no longer just residents of the Milky Way orbiting a galactic center. We are citizens of the Laniakea supercluster on a multi-billion-year journey toward its gravitational heart. This motion, however, does not mean we will eventually collide with the Norma cluster. The overall expansion of the universe is still carrying all the galaxies in Laniakea apart from one another, but the peculiar velocity induced by the Great Attractor is a significant modifier of that expansion on a local scale. It's a testament to the enduring power of gravity on the largest scales, a force that can orchestrate the motion of hundreds of thousands of galaxies, weaving them into a coherent flow amidst the relentless stretching of space. The story of the Great Attractor is ultimately the story of uncovering the invisible architecture of the cosmos, revealing that even the grand motion of our entire galaxy is but a single thread in the immense flowing tapestry of the cosmic web. From the immense gravitational tides that pull entire galaxy clusters, we now descend to the smallest and most elusive of cosmic speedsters. Fact 18 introduces us to neutrinos, the universe's very own ghost particles. These subatomic wraiths are produced in some of the most violent nuclear furnaces imaginable, from the heart of our Sun to the cataclysmic explosions of supernovae, and they travel at speeds so incredibly close to the speed of light that for the most energetic ones, the difference is practically zero. Yet, despite their staggering velocity and ubiquity, their most defining characteristic is their profound reluctance to interact with the rest of the universe, making them the ultimate cosmic escape artists. To understand the ghostly nature of a neutrino, you first have to appreciate its origins. These particles are born from the fundamental nuclear processes that power the cosmos. Inside the core of our Sun, where temperatures and pressures are crushing, hydrogen nuclei fuse together to form helium. In this process, a tiny fraction of the mass is converted directly into energy, but it also results in a surplus of particles called neutrons. To achieve stability, one of these neutrons can transform into a proton, and in doing so, it must spit out two particles, an electron and a neutrino. This specific type, an electron neutrino, then races out of the solar core, traveling at nearly the speed of light. The Sun is a veritable neutrino factory, producing so many that hundreds of trillions of them are passing through your body every single second, day and night, without you ever feeling a thing. This brings us to their most baffling property, their incredibly feeble interaction with normal matter. Neutrinos are so ethereal that they can fly through a light year of solid lead, a distance of about 9.5 trillion kilometers, with only a 50% chance of being stopped. They achieve this by being immune to both the electromagnetic force, which governs how light and charged particles interact, and the strong nuclear force, which binds atomic nuclei together. Neutrinos feel only the weak nuclear force, which operates at vanishingly short ranges, and gravity, which is utterly negligible for a particle so small. They are, in effect, perfect bullets slicing through planets, stars, and you with almost total impunity. This ghost-like behavior was a serious problem for physics for decades, as early detectors built to catch solar neutrinos were only finding about a third of the number predicted by our models of how the Sun works. Solving this solar neutrino puzzle required a deep and surprising revision to our understanding of particle physics itself. It turns out that neutrinos are not one single stable identity. They exist in three different types or flavors: the electron neutrino, the muon neutrino, and the tau neutrino. As a neutrino travels through space, it doesn't just remain as itself. It quantum mechanically oscillates, morphing between these three flavors in a constant probabilistic dance. The early detectors were only sensitive to the electron neutrino flavor. By the time solar neutrinos had traveled the 150 million kilometers from the Sun's core to Earth, about 2/3 of them had oscillated into the other two flavors, making them invisible to the original experiments. This discovery, which earned the Nobel Prize in Physics in 2015, proved that neutrinos, despite being nearly massless, do have a tiny, non-zero mass, a finding with profound implications for the fundamental laws of the universe. Catching these phantoms requires feats of engineering that border on the absurd. Because they so rarely interact, you need a colossal amount of detector material and to place it deep underground to shield it from the constant rain of other particles like cosmic rays. One of the most famous neutrino observatories is Super Kamiok, and in Japan, a cavern filled with 50,000 tons of ultra-pure water, lined with over 13,000 light-sensitive bulbs called photomultiplier tubes. When a rare neutrino does interact with an electron or a nucleus in the water, it can travel faster than the speed of light in that water, though still slower than light in a vacuum, and in doing so, it produces a faint, cone-shaped flash of blue light known as Cherenkov radiation. The detectors capture this beautiful, ethereal glow, allowing scientists to determine the direction and energy of the neutrino that caused it. Another colossal detector, the Ice Cube Neutrino Observatory, uses a cubic kilometer of pristine Antarctic ice as its detection medium, with sensors buried over a mile deep, turning the entire South Pole into a telescope for these ghostly particles. The ultimate neutrino spectacle occurred in 1987, when a star went supernova in the Large Magellanic Cloud, a neighboring galaxy. Hours before the visible light from the explosion reached Earth, a handful of neutrino detectors around the world registered a brief, simultaneous burst of about 24 neutrinos. While that number seems small, it was a monumental event in astronomy. These ghost particles, having traveled for 168,000 years, arrived just ahead of the light, providing the first direct confirmation that the core collapse of a massive star produces an unimaginable flood of neutrinos, carrying away 99% of the supernova's gravitational binding energy in a 10-second burst. For the first time, we had used neutrinos to observe a celestial cataclysm, marking the birth of multi-messenger astronomy and proving that these elusive speedsters are invaluable messengers from the most inaccessible and violent engines of the cosmos. And from the faint, ethereal whisper of neutrinos, we now turn to the universe's most deafening scream. Fact 19 introduces us to gamma-ray bursts, the single most powerful and violent class of explosions known to exist. For a few fleeting seconds, these events can outshine every star in every galaxy in the observable universe combined. Emitting more energy than our Sun will radiate over its entire 10 billion-year lifetime. All of that staggering power is concentrated into an incredibly narrow, ultra-relativistic jet of material and radiation, where matter is accelerated to an almost perfect 99.999% of the speed of light. These are not merely explosions, they are the universe's ultimate blowtorches, and their fleeting nature made them one of astronomy's greatest mysteries for decades. The story of their discovery is a classic Cold War tale of Serendou 0000 Pittis detection. In the late 1960s, the United States launched the Vela satellite series, a top-secret project designed to monitor for nuclear weapons tests in violation of the Atmospheric Test Ban Treaty. These satellites were equipped with gamma-ray detectors, as a nuclear detonation in space produces a characteristic flash of this high-energy radiation. To the surprise of the scientists analyzing the data, the satellites began detecting intense, brief bursts of gamma rays. They were coming not from Earth but from deep space, scattered randomly across the sky. For years, this data was kept classified, but once it was released, it presented a profound puzzle. What natural phenomenon could possibly produce such immense, focused energy in such a short amount of time and from such vast distances? It would take decades and a revolution in satellite technology to begin finding the answers. We now understand that there are two primary types of gamma-ray bursts, each with its own cosmic origin story, but both culminating in the birth of a new black hole. The longer bursts, lasting from 2 seconds to several minutes, are now linked to a specific kind of supernova, often called a collapsar or hypernova. This occurs when a truly massive star, dozens of times heavier than our Sun, reaches the end of its life. Its core, having fused elements all the way to iron, can no longer support itself against its own immense gravity and collapses directly into a black hole. What happens next is the key to the gamma-ray burst. As material from the star's outer layers rains down toward the newborn black hole, it doesn't fall straight in. Instead, it forms a whirling, superheated accretion disk. The insane physics around the black hole's poles then focuses and accelerates some of this infalling material into a pair of narrowly collimated jets. These jets, powered by the annihilation of neutrinos and antineutrinos or by intense magnetic fields, then blast their way out through the rest of the star, punching through its outer layers at near light speed. It is within these jets that the gamma rays themselves are produced. As internal shocks or magnetic reconnection, events accelerate particles to the point where they radiate the highest energy photons in existence. The second type, the short gamma-ray bursts, last for less than 2 seconds and pack their phenomenal energy into an even more concentrated package. The leading theory points to the merger of two ultra-dense stellar corpses, neutron stars or a neutron star and a black hole. For millions of years, such a binary pair spirals closer together, losing energy in the form of gravitational waves. In the final milliseconds before they collide, the tidal forces become unimaginably strong, tearing the neutron stars apart. The debris from this collision forms a hot, dense torus of material around the central object, which is almost instantly a black hole. Just as in the collapsar model, this accretion process powers the launch of relativistic jets. The merger of two neutron stars was confirmed as a source of short gamma-ray bursts in a historic event in 2017, when the gravitational wave signal from such a collision was detected, followed 2 seconds later by a short gamma-ray burst detected by the Fermi and Integral satellites. This multi-messenger observation tied these two cosmic phenomena together definitively, proving that these mergers are not only factories for gamma-ray bursts, but also the cosmic forges where heavy elements like gold and platinum are created and scattered into space. The reason a gamma-ray burst appears so phenomenally bright from Earth, even from billions of light years away, is a direct consequence of two key factors: the incredible energy involved and the razor-sharp focus of its jets. These are not spherical explosions. The energy is channeled into two opposing beams that might be only a few degrees wide. This means that instead of the energy being dissipated in all directions, it is concentrated into a very small solid angle, like the beam of a lighthouse compared to a bare light bulb. Furthermore, because the material in the jet is moving at such an extreme fraction of the speed of light, the radiation we observe is massively amplified by relativistic effects. The light is beamed toward us, its intensity dramatically boosted, and its frequencies shifted higher. We can only detect a gamma-ray burst if one of these devastatingly powerful beams happens to be pointed directly at Earth, which explains both their immense apparent brightness and their rarity. For every one we see, there are hundreds of others pointing in different directions, their cosmic screams lost in the darkness of intergalactic space. The aftermath of a gamma-ray burst is almost as fascinating as the initial explosion itself. As the relativistic jet plows into the surrounding interstellar medium, it creates a violent shock wave that continues to glow brightly across the electromagnetic spectrum for days or even weeks. This afterglow, which can be observed in X-ray, optical, and radio wavelengths, is what finally allowed astronomers to pinpoint the locations of these bursts and confirm their extragalactic origins. By studying the afterglow, scientists can determine the distance to the burst, the energy it released, and the properties of the environment it exploded into. A gamma-ray burst occurring within our own galaxy and pointed at Earth would be a catastrophic event for life on our planet. The initial blast of gamma rays would likely strip away the ozone layer, leading to a drastic shift in climate and exposing the surface to lethal levels of ultraviolet radiation from the sun. It is thought that such an event may have been responsible for one of the mass extinction events in Earth's distant past. Fortunately, the nearest potential progenitors are thousands of light years away, making such a direct hit an exceedingly remote possibility. These immense explosions thus serve as a humbling reminder of the universe's capacity for both creation and destruction on a scale that dwarfs our local celestial neighborhood. But how can we possibly see something move faster than the universe's ultimate speed limit? This brings us to a phenomenon so bizarre it seems to break the very rules we've established, yet it's a perfect illusion born from the geometry of relativity itself. Our 20th fact focuses on the brilliant quasar known as 3C273 and the mind-bending concept of superluminal motion. Discovered in 1963, 3C273 was the first quasar ever identified, a beacon so luminous it outshines entire galaxies from a distance of over 2.5 billion light-years. But beyond its sheer power, it presented astronomers with a stunning puzzle. Observations of its jet revealed blobs of plasma that appeared to be moving away from the core at several times the speed of light. This apparent faster-than-light motion is, of course, an illusion, but it's an illusion that reveals the profound strangeness of our universe when objects approach relativistic velocities. The key to unraveling this mystery lies not in the object's actual speed, but in the combination of its velocity and its angle relative to our line of sight. Imagine a distant quasar with a jet pointed almost but not quite directly at Earth. Now, picture a single blob of material within that jet being ejected from the core at 99.9% of the speed of light. As this blob travels along the jet, it emits light all along its journey. Here's where the cosmic trick occurs. The blob is moving almost as fast as the very light it emits. Consider the light it emits from point A near the quasar's core. That light begins its long journey toward Earth. A short time later, the blob has moved very close to us to point B and emits more light. Because the blob is traveling along a path that is angled toward us, the distance the second light signal has to travel to reach us is significantly shorter than the distance the first light signal had to cover. From our perspective, the time interval between the arrival of the two light signals, the pulse from point A and the pulse from point B, is dramatically compressed. We see the blob move from A to B in a much shorter time than it actually took in its own rest frame. When we then calculate its apparent speed by dividing the observed distance it appears to have traveled by our compressed measurement of time, the result can easily exceed the speed of light. It's a cosmic race where the object is essentially chasing its own light, and because it's taking a shorter path from our vantage point, it appears to win. A simple analogy can make this clearer. Imagine a runner on a long, straight track, but you are watching from a vantage point that is very close to the finish line, looking almost directly down the final stretch. The runner sprints from the starting blocks toward you at a constant, high speed. As they get closer, the angle at which you see them changes very little, making them appear to cover the last 100 meters of the track almost instantly from your perspective. If you only had your own timing and the apparent shift in their position against the distant background, you might calculate a speed that seems impossibly high. This is essentially what happens with a jet in a quasar like 3C273, but amplified by the mind-boggling velocities involved. This superluminal illusion, therefore, is not a violation of physics but a brilliant confirmation of it. The fact that we observe it so frequently in the jets of quasars and active galaxies provides powerful indirect evidence that the material in those jets is indeed being accelerated to velocities indistinguishable from the speed of light. It acts as a celestial speedometer, confirming the relativistic nature of these powerful outflows. The next time you hear about an object appearing to break the light barrier, you'll know it's not a flaw in Einstein's theories, but rather a breathtaking demonstration of their elegant and sometimes counterintuitive consequences, a trick of perspective played out on the grandest stage imaginable. But for all the fiery, high-energy processes we've explored, speed can also create some of the coldest environments in the cosmos. Our 21st fact takes us to the Boomerang Nebula, a stunning pre-planetary nebula located about 5,000 light-years away, where gas is being catapulted into space at a staggering 164 kilometers per second. This isn't just a fast outflow, it is the mechanism behind a profound cosmic chill, creating what is currently recognized as the coldest known natural place in the entire universe, with a temperature only a single degree above absolute zero. To grasp the sheer scale of this cold, consider that the empty space of the cosmic microwave background, the afterglow of the Big Bang itself, is a relatively balmy 2.7 degrees above absolute zero. The Boomerang Nebula is even colder. The story of this deep freeze begins with the death of a star, but not the violent supernova death of a massive giant. This is the more gentle, yet still dramatic, end-of-life transition for a star like our own Sun. In its final red giant phase, the star puffs off its outer layers in a series of slow, massive winds. What makes the Boomerang Nebula special is the star at its core, which is now a very hot, exposed stellar remnant. This tiny, intensely hot core is unleashing a far faster and more powerful wind than the initial slow wind, slamming into the earlier ejected material and shaping it. The incredible velocity of this fast wind is the direct cause of the nebula's record-breaking cold, and the principle at work is one you experience every day: adiabatic expansion, the same physics that cools the contents of an aerosol can when you spray it. Think about using a common spray can. As you press the nozzle, the compressed gas inside expands rapidly into the room. This sudden expansion forces the gas molecules to push against the surrounding atmospheric pressure, and in doing that work, they use up their own internal kinetic energy. Since temperature is fundamentally a measure of the average kinetic energy of molecules, this loss of energy translates directly into a dramatic drop in temperature. The can itself becomes noticeably colder to the touch. Now magnify that process to a cosmic scale. In the Boomerang Nebula, the gas ejected from the central star is expanding into the near-perfect vacuum of interstellar space at an astonishing speed. There is almost no pressure out there to resist it, so the expansion is incredibly efficient and rapid. The trillions upon trillions of gas molecules are all doing work to push this cosmic frontier outward, and in the process, they drain their collective energy down to an almost unimaginable low, plunging the entire nebula to a mere 1 degree above the theoretical minimum temperature, absolute zero. This rapid expansion is also what gives the nebula its distinctive shape and name. Early observations with ground-based telescopes in the 1980s showed a lopsided boomerang-like structure, which is how it earned its popular name. However, much more detailed observations from the Hubble Space Telescope in the 2000s revealed its true form. We now see it as a much more complex, hourglass-like shape, resembling a classic bow tie or a pair of nearly symmetrical lobes. This structure is the direct result of the central star's intense fast wind being funneled into 2 opposing directions, likely by a dense disk of dust and gas around its equator. This focused bipolar outflow is what accelerates the gas to such high velocities, creating the conditions for its profound cooling. It's a beautiful and poignant example of stellar death, where the final breaths of a star are not just scattered gently into the void, but are violently and rapidly accelerated, sculpting the surrounding envelope into an ethereal, freezing cold monument. While our journey has taken us across billions of light years to witness the universe's natural particle accelerators, humanity has not been content to simply observe from the sidelines. Fact 22 brings our quest for ultimate speed down to Earth, to a massive circular tunnel buried 100 meters beneath the French-Swiss border. This is the Large Hadron Collider, or LHC, the most powerful and complex machine ever built, and it is here that we deliberately smash together tiny protons at a staggering 99.999991% of the speed of light. This is not just a celebration of raw velocity. It is a testament to human curiosity and ingenuity, a machine designed to pry open the deepest secrets of the cosmos by recreating, for a fleeting instant, the conditions of the universe's very first moments. To appreciate the sheer scale of this endeavor, you have to step back and look at the machine as a whole. The LHC is a circular ring with a circumference of 27 kilometers. It is not a simple vacuum tube. It is a cathedral of technology, a precision instrument where two beams of protons are sent flying in opposite directions through a pipe colder and emptier than intergalactic space. These protons don't just get up to speed on their own, they are put through a veritable particle boot camp. The process begins with a simple bottle of hydrogen gas. The atoms are stripped of their electrons, and the resulting protons are injected into a chain of smaller accelerators that act like a cosmic relay race, each one boosting the particles to a higher energy before handing them off to the next. By the time the twin proton beams are injected into the main LHC ring, they are already traveling at a respectable fraction of light speed. But the real magic, the final push to within a whisper of the cosmic speed limit, happens in that 27-kilometer circle. This final, phenomenal acceleration is made possible by one of the greatest engineering marvels of the machine. Its superconducting magnets, lining the entire tunnel, are over 1,600 of these behemoths, each one a masterpiece of cryogenics and electromagnetic design. To keep the protons, which are positively charged, racing in a perfect circular path, the LHC needs immensely powerful magnetic fields to bend their trajectory. These magnets are not your ordinary bar magnets. They are electromagnets, but they operate in a superconducting state. This requires cooling them with liquid helium to a temperature of -271 degrees Celsius, which is actually colder than the void of outer space. At this extreme cold, the magnet's wires lose all electrical resistance, allowing them to carry immense electrical currents, over 12,000 amperes, without overheating or losing energy. This creates a magnetic field over 100,000 times stronger than Earth's, a force so powerful it can bend a beam of these relativistic protons into a tight circle. Without these magnets, the protons would simply fly off in a straight line and slam into the tunnel wall in an instant. Once the two counter-rotating beams are packed with trillions of protons each and accelerated to their peak energy, they are steered to cross paths at 4 specific points around the ring. These are the collision points, the hearts of the giant detectors with names like Atlas and CMS. Here, the beams are focused down to a width thinner than a human hair, and at the precise moment, magnets nudge the beams so that bunches of protons cross. Even with trillions of particles in each beam, protons are so fantastically small that most will pass right through each other without a touch. But at these designated interaction points, the beams are so dense that hundreds of millions of collisions occur every second. When two protons traveling in opposite directions at 99.9999991% of the speed of light actually hit head-on, the energy of that impact is concentrated into a space a million times smaller than a mosquito. The result is a miniature fireball of pure energy, a temperature over 100,000 times hotter than the core of the Sun, recreating the conditions that were universal just a trillionth of a second after the Big Bang. In that spectacular instant of creation, the kinetic energy of the colliding protons is converted directly into matter, following Einstein's famous equation, E equals mc squared. For a fleeting moment, new, often incredibly massive and exotic particles that have not existed naturally since the universe's infancy blink into existence. This is the true purpose of the LHC, to be a time machine. We cannot travel back to the first moments of the cosmos, but we can recreate its energy scale and see what particles emerge from that primordial soup. It was in these very collisions that the Higgs boson was discovered in 2012, a landmark achievement that confirmed the mechanism which gives all fundamental particles their mass. Every time the beams collide, we are conducting an experiment that probes the fundamental laws of nature, searching for hints of dark matter, extra dimensions, or reasons for the overwhelming matter-antimatter asymmetry in our universe. The protons racing around the LHC may be the fastest human-controlled objects in history, but their true value is not in their speed alone. It is in the profound cosmic secrets they unlock every time they are made to collide in a brilliant, microscopic echo of the universe's violent birth. Now, just when we think we understand the grand motions of the cosmos, from our solar system's orbit to our galaxy's drift toward the Great Attractor, astronomers have stumbled upon something that challenges the very definition of our observable universe. Fact 23 introduces us to a phenomenon even more perplexing than the Great Attractor, something known as the dark flow. This is the mysterious, controversial observation that not just a few galaxies, but entire clusters of galaxies, each containing thousands of individual systems, appear to be caught in a coherent, high-speed stream, all moving in the same direction toward a point on the sky that lies far beyond the edge of everything we can see. It's as if the entire cosmic tapestry is being tugged by a force from the great, unseen beyond. The discovery of the dark flow came from an incredibly precise analysis of the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. This radiation is not perfectly uniform. It has tiny millionth of a degree temperature variations that form a map of the infant universe. As galaxy clusters travel through space, the hot, thin gas trapped within their gravitational pull interacts with this background radiation in a specific way. The movement of a cluster through this radiation creates a slight distortion known as the kinematic Sunyaev-Zeldovich effect, a minute shift in the temperature of the microwaves that allows scientists to measure the cluster's peculiar velocity, its motion relative to the overall expansion of the universe. When a team led by Alexander Kashlinsky began analyzing data from the Wilkinson microwave anisotropy probe, they expected these velocities to be random, canceling each other out over large distances. Instead, they found a shocking pattern. Clusters scattered across billions of light-years were all streaming in the same direction at speeds of up to 1,000 kilometers per second. A coordinated motion on a scale that should be impossible according to our standard model of cosmology. The core of the problem lies in the cosmological principle, a fundamental tenet of modern physics which states that the universe on large scales is homogeneous and isotropic. This means it should look roughly the same in all directions and have no preferred center or edge. The gravitational forces that cause motions like our journey toward the Great Attractor are generated by the uneven distribution of matter within our observable universe, the cosmic web of superclusters and voids. But the dark flow appears to be different. The sheer scale of this coordinated motion, stretching to the very limits of our observation, suggests the gravitational pull responsible for it must originate from a mass so enormous and so distant that it lies outside our cosmic horizon. This is the truly radical implication. The flow seems to be sourced by something that is not, and has never been, a part of our observable universe since the Big Bang. This is where the hypothesis ventures into the realm of the extraordinary, pointing toward the existence of a multiverse. One of the leading explanations for the dark flow is that the gravitational tug is coming from another universe, a separate bubble of space-time born in a different Big Bang event, residing in an eternally inflating megaverse. According to this theory, the rapid inflation that created our universe did not happen just once, but is ongoing in a vast, higher-dimensional landscape, constantly spawning new universes like bubbles in a boiling pot. If another of these bubble universes happen to form relatively close to ours in this greater multiverse landscape, its immense mass, the collective gravity of all its stars, galaxies, and dark matter, could, in principle, reach across the void and exert a tidal force on our entire cosmic domain. The dark flow, in this interpretation, would be the first empirical evidence for something beyond our cosmos, a cosmic current induced by a neighboring reality. Of course, a claim this profound is met with intense scrutiny and skepticism within the scientific community. Critics have pointed to potential systematic errors in the data analysis or unaccounted for foreground effects that could mimic the signal. Some suggest that the flow, while real, might still be explained by an unimaginably vast, undiscovered concentration of mass within our own universe, perhaps a structure so colossal it challenges our understanding of how the cosmic web can form. The debate is ongoing, and subsequent studies with newer data from the Planck satellite have produced conflicting results, with some analyses supporting the original finding and others failing to detect the signal with the same strength. This scientific tension is a healthy and necessary part of the process, pushing observers and theorists to refine their methods and models. Ultimately, whether the dark flow is confirmed or eventually explained away, its investigation has already expanded the boundaries of cosmological thought. It forces us to confront the humbling possibility that our universe is not an isolated island, but part of a far grander multi-cosmic archipelago. The idea that we could potentially detect the gravitational fingerprint of another universe simply by mapping the subtle drift of galaxy clusters is a testament to the power and ambition of modern science. It transforms the concept of the multiverse from a purely theoretical speculation into something that might, one day, be tested and observed. The dark flow represents the ultimate cosmic mystery, a whisper from the other side of reality, challenging us to consider that the greatest forces shaping our cosmic destiny may not lie within the world we see, but just beyond its furthest edge. But if a regular pulsar is a cosmic flywheel, then a magnetar is that same flywheel sheathed in the most terrifying magnetic field imaginable. Our 24th fact plunges us into the realm of these magnetic monsters, a special class of neutron stars where the magnetic fields are so obscenely powerful that they literally warp the very fabric of reality around them. To grasp the scale, consider that a hospital MRI machine operates with a magnetic field of about 1 to 3 Tesla. A typical neutron star might have a field of 100 million Tesla. A magnetar, however, possesses a magnetic field of 1,000 trillion Tesla. If a magnetar were located halfway between the Earth and the Moon, its magnetic field would effortlessly erase the data from every credit card and hard drive on our planet. It is a level of power that transforms the space around the star into a bizarre quantum laboratory, where the vacuum itself is polarized and light is forced to travel in strange, twisted ways. These inconceivable fields are the product of the star's incredibly dense, superconducting interior. During the supernova collapse that creates the neutron star, the original star's magnetic field is compressed and amplified to an almost unimaginable degree. In a magnetar, theorists believe a powerful dynamo effect takes over, where the convecting, ultra-hot fluid of neutrons and protons in the newborn star's core acts like a massive electrical generator, amplifying the magnetic field to these ludicrous levels in a matter of seconds. The energy stored in this magnetic cocoon is staggering, accounting for a significant portion of the star's total energy budget. This immense internal stress constantly seeks a way to release itself, and that is where the star's rigid crystalline crust comes into play. This crust, believed to be perhaps a kilometer thick and harder than any known substance, is under perpetual, unimaginable strain, bent and stressed by the twisted magnetic fields frozen within it. This sets the stage for one of the most violent events in the present-day universe, the starquake. Picture the magnetar's crust not as a tranquil surface, but as a brittle, rigid shell under immense pressure, like the tectonic plates of Earth but under forces quadrillions of times stronger. As the internal magnetic fields evolve and shift, they exert unbearable stress on this crust. Eventually, something has to give. The crust suddenly fractures and cracks, shifting in a jarring, global seismic event. This is a starquake. The energy released in a single one of these events is comparable to a magnitude 32 earthquake on the Richter scale, a scale where each whole number increase represents a 32-fold rise in energy. The sheer power is incomprehensible. It is enough to make the entire star, this city-sized ball of ultra-dense matter, ring like a bell, oscillating and vibrating at frequencies of hundreds of hertz. The consequences of a starquake are immediate and spectacular. The sudden crustal movement violently shakes the magnetic field lines anchored to it. Think of it like plucking a gigantic cosmic guitar string made of pure magnetism. This rapid distortion of the magnetic field generates an immense electric field, which in turn accelerates any free electrons or protons in the vicinity to velocities indistinguishable from the speed of light. These ultra-relativistic particles then spiral along the curved magnetic field lines, and in doing so, they radiate away their energy in a brilliant flash of X-rays and gamma rays. This is the signature of a magnetar flare, a sudden, short, and intensely luminous burst of high-energy radiation that can, for a fraction of a second, outshine every other X-ray source in our entire galaxy combined. We have been fortunate, or perhaps unfortunate, enough to witness the effects of such an event from a safe distance. On December 27, 2004, a colossal blast of gamma rays and X-rays swept through our solar system, temporarily ionizing the upper layers of Earth's atmosphere and saturating the detectors of every spacecraft designed to observe such phenomena. The source was a magnetar named SGR 1820-14, located about 50,000 light-years away on the other side of the Milky Way. The flare was so powerful that for 0.2 of a second, it released more energy than our Sun has emitted over the last 300,000 years. This specific event, now known as the Christmas Star or the Great Flare of 2004, is believed to have been triggered by a catastrophic starquake that rearranged the magnetar's colossal external magnetic field. While it lasted less than a second, it provided astronomers with an unprecedented look at the raw, unadulterated power that these magnetic leviathans can wield. A stark reminder that the universe is home to forces capable of unleashing planet-devastating energies from clear across the galaxy. Think of the Sun not as a stationary beacon, but as a great ship sailing through the galactic ocean. As it moves, it doesn't travel through a perfect void. It plows through the interstellar medium, a thin soup of gas and dust that fills the space between the stars. This constant motion, at a brisk 230 kilometers per second relative to our local galactic neighborhood, creates a fascinating and colossal structure that envelops our entire solar system. This is our 25th fact, the heliosphere and its bow shock, a protective bubble and a cosmic wave that defines the very boundaries of the Sun's influence, a frontier that our most distant robotic envoys are only now beginning to cross. The engine of this vast structure is the solar wind, a relentless supersonic stream of charged particles, primarily protons and electrons, that blows outward from the Sun in all directions. This wind carries with it the Sun's magnetic field, inflating a gigantic bubble in the interstellar medium called the heliosphere. inside this bubble, the solar wind blows freely. Outside, the interstellar medium exerts its own pressure. The boundary where these two forces meet is not a hard wall, but a complex series of layers and shock waves. As the heliosphere rams through the galactic material, it behaves exactly like a boat speeding through water. Just as a boat pushes a bow wave ahead of it, the heliosphere creates a similar, though invisible, structure in the plasma of space. This is the bow shock, a turbulent region where the incoming interstellar material is suddenly slowed, heated, and compressed as it collides with the outward pressure of the heliosphere. The shape and nature of this boundary are not fixed. They are dynamic, breathing in and out with the 11-year cycle of solar activity. When the Sun is at its most active, with more frequent solar flares and coronal mass ejections, the solar wind is stronger and denser, pushing the boundary of the heliosphere further out, inflating our protective bubble. During solar minimum, when the wind is weaker, the bubble contracts, allowing more of the raw interstellar environment to press inward. This constant interplay acts as a crucial shield for life on Earth. The heliosphere buffers our solar system from the majority of galactic cosmic rays, those high-energy atomic nuclei accelerated by distant supernovae and other cataclysms. Without this magnetic bubble, the flux of these damaging particles reaching our planet would be significantly higher, with potential implications for climate and the evolution of life. It is our first and most important line of defense against the broader galaxy. For decades, the structure of the heliosphere was purely theoretical, a concept drawn on chalkboards. That all changed with the twin Voyager probes launched in 1977. Their primary missions were to study the outer planets, but their epic journeys continued long after their planetary flybys were complete. They became our first interstellar scouts, carrying with them the golden records, messages to any potential finders that speak of our world and our species. As they raced toward the void, their instruments began to sense the faint edges of the Sun's realm. The first major milestone was crossing the termination shock, the point where the solar wind slows from supersonic to subsonic speed as it begins to feel the pressure of the interstellar medium. Voyager 1 crossed this boundary in 2004, and Voyager 2 followed in 2007, confirming that our heliospheric bubble is not perfectly round but is squashed and asymmetric. The next and even more profound frontier was the heliopause. This is the true boundary, the outer skin of the heliosphere where the outward pressure of the solar wind finally balances the inward pressure of the interstellar wind. Beyond this point, the environment is dominated by material from between the stars. In August of 2012, Voyager 1's instruments recorded a dramatic drop in solar particles and a corresponding increase in galactic cosmic rays. It had crossed the heliopause and entered interstellar space, becoming the first human-made object to do so. Voyager 2 achieved the same feat in November 2018, providing a second crucial day to point from a different location that revealed the heliosphere's complex and dynamic shape. The data from these two intrepid probes has been revolutionary. It showed that the bow shock ahead of our heliosphere might be more of a bow wave, a smoother transition than the violent shock once imagined, and that the magnetic field of the local interstellar medium plays a far greater role in sculpting our cosmic home than we ever knew. These two tiny spacecraft, now over 15 billion miles from home with fading power, are our fingertips touching a boundary that, until very recently, was just a line on a diagram, teaching us that the Sun's journey is not a silent one, but one that creates a vast protective wake as we cruise through the galaxy. Just when we thought the collision of black holes was the ultimate expression of gravitational waves, the universe unveiled another, even more glittering cataclysm. Fact 26 brings us to the kilonova, a spectacular explosion born from the final, fatal embrace of two neutron stars. Imagine two city-sized objects, each containing more mass than our entire Sun, compressed into a density so extreme that a single teaspoon would weigh billions of tons. Now picture these two incomprehensibly dense spheres locked in a gravitational dance, spiraling closer and closer over millions of years until they finally collide. The merger is not a simple collision. It is a complex multi-messenger event that forges the very elements we wear as jewelry, unleashes a blitz of high-energy radiation, and sends literal ripples through the fabric of space-time itself. The prelude to this cosmic spectacle is a relentless in-spiral driven by the emission of gravitational waves. As the two neutron stars orbit each other, they lose orbital energy by radiating these ripples in space-time, causing their paths to slowly decay. In the final moments, this process accelerates dramatically. The stars whip around each other thousands of times per second, reaching velocities a significant fraction of the speed of light, churning the space-time around them into a frenzy just before impact. The actual moment of merger is a violent and messy affair. The two ultra-rigid stellar corpses don't just cleanly combine, they tear each other apart under immense tidal forces, shredding a small but significant fraction of their material into a hot, dense cloud of neutron-rich debris that forms a rapidly spinning torus around the central merger remnant. For a brief instant, this remnant is an object more massive than any single neutron star can be, and it must immediately decide its fate, collapsing almost instantly into a black hole or, for a fleeting moment, existing as an immensely massive hypermassive neutron star. It is from this chaotic debris disk that the true magic of the kilonova unfolds. The material ejected from the merger is an alchemist's dream, a soup of free neutrons and atomic nuclei. In this environment, a rapid-fire nuclear capture process takes place, known as the Rapid Neutron Capture Process, or R process. Atomic nuclei are bombarded by a flood of neutrons so dense that they stick to the nuclei faster than the resulting unstable isotopes can decay. This process builds up the atomic nucleus, climbing the periodic table in a matter of seconds to create the heaviest elements in nature. It is here, in the fiery aftermath of a neutron star collision, that vast quantities of gold, platinum, uranium, and other rare heavy elements are forged. A single kilonova event can produce hundreds of times the mass of our entire planet in pure gold and other precious elements, scattering this newly minted treasure out into the galaxy to one day be incorporated into new stars, planets, and perhaps even life. The observable signature of this elemental factory is the kilonova glow itself. The radioactive decay of all these newly created unstable elements heats the expanding cloud of ejecta, causing it to shine brightly for several days. Unlike a supernova, which can outshine a galaxy for weeks, a kilonova is relatively dim and short-lived, and it has a distinct reddish color. This color comes from the specific atomic properties of the lanthanides, a group of heavy elements produced in the R process, which have complex atomic structures that block and redden the escaping light. This unique transient glow is the telltale sign that astronomers look for to confirm that a neutron-star merger has occurred. The cataclysm does not end with the kilonova glow. The merger also powers two of the most energetic phenomena we have already discussed. As the central black hole forms and begins to devour the surrounding accretion disk, the same basic engine that powers quasars and blazars kicks into action on a smaller but incredibly intense scale. Magnetic fields and the immense gravitational energy funnel a portion of the infalling material into two ultra-relativistic jets, screaming outward from the poles of the newborn black hole. If one of these jets is pointed fortuitously in our direction, we observe it as a short gamma-ray burst, a blinding flash of the highest energy photons that lasts for less than 2 seconds but outshines entire galaxies for that fleeting moment. Simultaneously, the violent dynamics of the merger itself, the final orbits, and the collapse produce a powerful, distinct burst of gravitational waves, a high-frequency chirp that is the audio signature of this cosmic collision. The historic event that brought all these pieces together was detected on August 17, 2017. The LIGO and Virgo gravitational wave observatories recorded a signal consistent with two neutron stars merging, and just 2 seconds later, the Fermi and Integral Space Telescopes observed a short gamma-ray burst from the same patch of sky. This triggered a global astronomical hunt, and within hours, telescopes around the world and in space had pinpointed the source. A new point of light in the galaxy NGC 4993, about 130 million light-years away. What they observed over the following days was the definitive kilonova, its light evolving in brightness and color exactly as predicted, transitioning from blue to red as the cloud of heavy elements expanded and cooled. This single event, known as GW1 70817, was a watershed moment in astronomy. It confirmed the long-held theory that neutron star mergers are the primary cosmic source for the R-process elements. It definitively linked short gamma-ray bursts to these mergers, and it marked the first time a cosmic event had been observed in both gravitational waves and light, truly launching the era of multi-messenger astronomy and giving us a complete multi-sensory picture of one universe's most productive and violent factories. Just as we begin to think we have a handle on the incredible speeds and energies of natural cosmic events, we are reminded that the universe might also contain evidence of intelligence, a possibility that forces us to consider an entirely different kind of velocity. Our 27th fact takes us from the certainties of physics to one of the most enduring mysteries in the search for extraterrestrial intelligence, the WOW signal. Detected in 1977 by the Big Ear radio telescope at Ohio State University, this was a powerful, narrowband burst of radio waves that lasted for 72 seconds and appeared to originate from the direction of the constellation Sagittarius. What made it extraordinary was that it matched the precise expected signature of an artificial, interstellar transmission. While the radio waves themselves traveled at the speed of light, as all electromagnetic radiation must, the hypothetical source of that signal, if it was indeed artificial, opens up a fascinating realm of speculation about the possible motion and technology of a civilization capable of such a feat. The raw power of the signal is the first clue to its potentially artificial nature. The Big Ear telescope used a measurement system called signal-to-noise ratio, and the WOW signal registered at a value of 30 sigma, an off-the-charts intensity that was many times stronger than the background noise of space. To project a signal that strong across the cosmic distances separating stars would require a transmitter far beyond anything humanity has ever built. A common comparison is that the signal was as powerful as if someone had focused the entire output of a large nuclear power plant exclusively into a narrowband radio beacon and aimed it directly at us. The sheer energy requirement alone suggests a technological capability of a scale we can scarcely imagine, a civilization that has mastered power generation and antenna technology on a planetary or even system-wide level. Now consider the implications of motion. The Big Ear telescope was fixed to the Earth, scanning the sky as our planet rotated. The signal rose to peak intensity and then faded away over exactly 72 seconds, which was the precise window of time a stationary point source would be in the telescope's beam. This perfect timing is what makes the signal so compelling, but it also locks the source to the celestial sphere. If the transmitting civilization was on a planet orbiting a star, that star has its own proper motion through the galaxy. Our own sun, as we've learned, moves at 230 kilometers per second. Their star would be moving at a different velocity and direction. Their planet would be orbiting that star, and their transmitter might even be on a spacecraft. All of these motions would introduce a Doppler shift and a slight drift in the signal's frequency over time, effects that our most sensitive modern searches for extraterrestrial intelligence actively look for. The WOW signal was so brief that we couldn't measure any drift, leaving the velocity of its source a complete mystery. Was it broadcast from a planet circling a calm, older star, or perhaps from a massive interstellar vehicle on a long-term voyage across the galaxy. The lack of data leaves the question tantalizingly open. This leads to the profound technological implications of a broadcast that is both incredibly powerful and potentially mobile. To aim such a focused signal accurately at a distant star system or worse, to track a moving target like our solar system as it speeds through the galaxy, would require a guidance and targeting system of phenomenal precision. We are not talking about aiming at a stationary bullseye from a stable platform. This would be like trying to hit a speeding bullet with another bullet, while both are traveling on separate, curving racetracks across a distance of thousands of light years. The computational power and navigational awareness needed to calculate the correct aim point, accounting for light travel time and the relative motions of both stars over centuries or millennia, is staggering. It implies a deep understanding of celestial mechanics on a galactic scale and an engineering prowess that could build structures capable of maintaining that lock for the duration of the transmission. Furthermore, the very nature of the signal suggests a deliberate attempt to be noticed. A narrowband signal is inefficient for merely communicating within a civilization. It is the ideal way to shout, "We are here." Across the void, as it is easily distinguishable from the broadband noise of natural cosmic objects, the decision to broadcast in this way with such immense power could reflect a society that has reached a stable, long-term technological plateau, one that has the resources and the foresight to engage in a patient million-year project of cosmic greeting. Or perhaps the signal was not a deliberate message at all, but a powerful byproduct of their own technology, a kind of radar for mapping asteroids or an energy beam for propelling spacecraft that just happened to sweep past our location. The possibility that we intercepted a leakage signal from their everyday activities is in some ways even more mind-boggling, as it would imply that such prodigious power output is commonplace for them. Despite numerous attempts to redetect the signal from the same region of space, including recent efforts to link it to a specific sun-like star, the WOW signal has never been heard again. Its one-time, enigmatic nature is what solidifies its place in the annals of cosmic mystery. It stands as a singular event, a perfect candidate that fits the profile of an artificial signal in almost every way, yet one that remains stubbornly unconfirmed. It teaches us a crucial lesson about the challenges of SETI, the search for extraterrestrial intelligence. The cosmos is vast not just in space but in time. A civilization might broadcast for only a brief window in its history, or it might direct its signals in narrow beams that sweep across the galaxy like a lighthouse, illuminating any given star system for only a moment. The WOW signal could have been that one brilliant, fleeting moment for us, a flash in the cosmic dark that challenges our anthropocentric view and forces us to contemplate the incredible velocities, both physical and technological, that another intelligence in the galaxy might have achieved. While we contemplate signals that might cross the interstellar void, humanity has already launched its own silent messengers on the same incredible journey. Our 28th fact celebrates the Pioneer and Voyager probes, the first human-built objects to achieve the phenomenal speed necessary to escape the Sun's gravitational grip entirely. These are not merely satellites orbiting our planet or even our star. They are interstellar travelers carrying with them the story of their origin out into the vast ocean between the stars. Their velocity is their ticket to eternity, a momentum that will carry them through the galaxy for billions of years, long after our own star has faded. The key to their incredible escape lies not in colossal rocket engines that burned for days, but in a masterful application of celestial mechanics known as the gravity assist. Think of it as a cosmic slingshot, a way for a spacecraft to steal a tiny fraction of a planet's orbital momentum to dramatically boost its own speed without using a single drop of fuel. The Voyager missions, in particular, executed this technique with breathtaking elegance. Their trajectory was carefully calculated to take advantage of a rare planetary alignment that occurs only once every 175 years. This grand tour allowed Voyager 2 to fly by Jupiter, Saturn, Uranus, and Neptune in a single, continuous mission, using each encounter as a powerful gravitational whipcrack to propel it onward to the next destination and ultimately toward interstellar space. At Jupiter, for instance, the planet's immense gravity pulled the spacecraft in, accelerating it as it fell toward the giant. As Voyager swung around the planet, it was flung outward on its new path, having gained a significant portion of Jupiter's own orbital velocity around the Sun. This single maneuver added enough speed to shave years off the journey to Saturn, and each subsequent flyby compounded the effect. The Voyagers were not just flying past these worlds, they were using them as gravitational stepping stones to leap out of the solar system. The Pioneer probes, the trailblazers that preceded the Voyagers, achieved their escape velocity through a more direct but equally effective route. Launched on faster, more powerful trajectories, they too received critical gravity assists from Jupiter that hurled them outward toward the boundaries of the Sun's influence. The result of these maneuvers is a set of velocities that are permanently greater than the solar system's escape velocity at their distance. Voyager 1 is currently the fastest and farthest of the group, racing away from the Sun at over 61,000 kilometers per hour. While this is a tiny fraction of light speed, it is more than enough to overcome the Sun's pull. They are like stones thrown so hard that they will never fall back to Earth, their arc extending forever into the galactic dark. Their paths are now hyperbolic, open-ended curves that will never loop back, marking a permanent departure from our celestial neighborhood. But these spacecraft are more than just inert hunks of metal. They are time capsules and greeting cards rolled into one. The most famous of these are the golden records aboard the Voyager probes. These are not digital files, but 12-inch gold-plated copper discs containing a carefully curated sampling of the sights and sounds of Earth. They carry greetings in 55 languages, the brainwaves of a person in love, the sounds of waves, wind, and thunder, and a diverse collection of music from around the world, from Bach and Beethoven to Chuck Berry and traditional scenic percussion. They also contain 115 images encoded in analog form, depicting everything from mathematical diagrams and DNA structures to photographs of human beings, our planet's landscapes, and our daily life. The records are accompanied with symbolic instructions on how to play them, using a cartridge and stylus also provided on the spacecraft's exterior. The entire assembly is a message in a bottle on an unimaginable scale, a testament to a species on a small world that looked up and decided to cast its story adrift on the tides of the galaxy. The ongoing journeys of these probes are a continuous source of scientific discovery, even decades after their primary planetary missions ended. As we discussed with the heliosphere, their most profound recent achievement has been crossing the final boundary of the Sun's influence. Voyager 1's passage through the heliopause in 2012 and Voyager 2's in 2018 have given us our first direct measurements of the true interstellar medium. Their instruments, though powered down one by one to conserve dwindling nuclear power, continue to send back data on the magnetic fields and cosmic rays in this uncharted territory. They are our frontline scouts, reporting back from a region no human-made object has ever been before. Their very existence at such distances is a staggering feat of engineering longevity, having operated for over 45 years on a combination of precise planning, robust design, and the slow, steady decay of plutonium-238. The ultimate fate of these interstellar envoys is as poetic as their mission. They will continue on their silent trajectories, their power sources eventually going dark, their instruments falling forever silent. But their journey will not end. They will drift through the Orion arm of our galaxy, completing an orbit around the galactic center every 225 million years. The probability of them ever being found is astronomically small. Space is too vast and the probes are too tiny. Yet they carry with them the potential to outlast humanity itself and even our planet. In about 5 billion years, as the Sun begins its death throes and expands into a red giant, engulfing the inner planets, the Voyager and Pioneer probes will be far away, untouched by the inferno. They will continue on as permanent, silent artifacts of a civilization that once existed around a star in the Milky Way, carrying a fragile record of what we were, a whisper of life and curiosity in the overwhelming cosmic silence. Now, let's dive into one of the most visually and physically spectacular environments in the universe, the inner sanctum of an accretion disk. Picture a whirlpool of incandescent gas, a cosmic maelstrom swirling around a black hole or neutron star. But this isn't a placid, orderly rotation like the rings of Saturn. As you approach the central monster, the velocities become so extreme that the very laws of Einstein's relativity begin to paint the scene in bizarre and dramatic ways. The inner regions of these disks don't just orbit quickly, they whip around at a significant fraction of the speed of light, creating a cosmic ballet where space and time themselves are twisted into knots, and matter glows with the heat of its own frantic motion under the influence of gravity's ultimate grip. This incredible speed in the inner disk arises from the need to balance an unimaginable gravitational pull. For a particle to maintain a stable orbit, its orbital velocity must be high enough to counteract the relentless inward tug of the central object's gravity. Closer to the center, that gravitational pull becomes overwhelmingly strong, demanding orbital velocities that climb to 30, 50, or even 80% of the speed of light. To put that into a tangible image, imagine a cloud of superheated plasma completing a full orbit around a black hole in the time it takes you to blink, tracing a circular path at tens of thousands of kilometers per second. This isn't empty space whirling around. It's a thick soup of ionized gas where atoms are torn apart into their constituent particles, creating a friction-filled, turbulent environment that glows with the intense energy of a billion suns. The friction within the disk, generated by particles jostling against each other at these phenomenal speeds, heats the material to temperatures of millions of degrees, causing it to radiate powerfully across the electromagnetic spectrum, from X-rays to gamma rays. This relativistic motion doesn't just make the disk bright, it fundamentally alters the very light that escapes from it, creating two distinct and powerful observational effects that astronomers use as their primary tools to study these invisible objects. The first is Doppler boosting, also known as Doppler beaming. Imagine a single blob of this glowing material on one side of the disk, moving at near light speed directly toward us as it orbits. Because of its motion, the light waves it emits are compressed, similar to how the sound of an approaching ambulance siren has a higher pitch. This relativistic compression shifts the light to higher frequencies and, crucially, makes the blob appear significantly brighter from our viewpoint. At the same instant, a blob on the opposite side of the disk, moving away from us at a comparable speed, has its light stretched to lower frequencies and dramatically dimmed. The result is that the accretion disk doesn't appear as a uniform, symmetrical ring. Instead, it looks lopsided, with one side blazing brilliantly and the other appearing faint and reddish. This asymmetric glow is a direct and measurable signature of the relativistic velocities at play, a cosmic lighthouse effect imprinted on the very structure of the disk's light. The second critical effect is gravitational redshift, a phenomenon predicted by Einstein's general theory of relativity that is separate from the Doppler effect. As light climbs out of the deep gravitational well of the central black hole or neutron star, it loses energy. Since the energy of light is tied to its frequency, this loss of energy causes the light to shift toward the red end of the spectrum. The stronger the gravity, the more extreme the redshift. In the inner region of an accretion disk, where the gravitational field is most intense, this effect is profound. The light we receive from that area is systematically redder than it was when it was emitted. When astronomers observe the spectrum of an accretion disk, they don't see a single clean line. Instead, they see a broad, smeared outline that is skewed and distorted, blue-shifted on the side coming toward us due to Doppler boosting, and red-shifted on the receding side and from the deepest gravitational well. By carefully analyzing the precise shape and skew of this broad spectral line, scientists can perform remarkable feats of cosmic deduction. They can map the velocity of the orbiting gas, determine the spin of the central black hole, and even probe the structure of spacetime just outside the event horizon, turning the distorted light into a precise diagnostic tool for the most extreme environments in existence. What makes these relativistic effects so invaluable is that they allow us to study objects that are, by their very nature, invisible. A black hole emits no light of its own, and a neutron star is often too small and distant to resolve directly. The accretion disk, however, is a luminous proxy, its light encoded with the fingerprints of the monster it orbits. By observing the dance of this light, the rhythmic brightening and dimming from Doppler boosting and the telltale redshift, astronomers can effectively see the black hole's influence. They can measure its mass with incredible precision and, even more impressively, determine its spin. A spinning black hole, described by the Kerr metric, drags the very fabric of spacetime around with it, an effect known as frame dragging. This pulls the inner edge of the accretion disk closer to the event horizon, allowing the gas to orbit at even higher velocities. A rapidly spinning black hole will therefore produce more extreme Doppler boosting and broader spectral lines than a non-spinning one. In this way, by reading the subtle language written in the distorted light of the accretion disk, we can uncover the secrets of the most enigmatic objects in the cosmos, using the violent, relativistic motion of matter on the brink of oblivion to illuminate the properties of the darkness itself. And so, after our grand tour of the universe's natural speed demons, from particles accelerated to a hair's breadth, from light speed to entire galaxies caught in a cosmic current, we arrive at our final, speculative, and utterly mind-bending fact: the theoretical Alcubierre warp drive. This is not science fiction, but a mathematical solution to Einstein's own field equations of general relativity, a concept that offers a potential blueprint for achieving faster-than-light travel without the ship, or anyone inside it, ever breaking the cosmic speed limit. Instead of trying to push a vessel through space faster than light, an obvious impossibility for anything with mass, the Alcubierre drive proposes a far more clever solution: to manipulate the very fabric of spacetime itself, bringing your destination to you. The core idea, first proposed by Mexican physicist Miguel Alcubierre in 1994, is to create a warp bubble around a spacecraft. Inside this bubble, spacetime would remain perfectly flat and normal. The crew would experience no acceleration forces, no relativistic time dilation, and they would be at rest relative to their local environment. The magic happens in the spacetime fabric just outside the bubble. The drive would work by contracting the spacetime immediately in front of the ship, pulling the destination closer, while simultaneously expanding the spacetime immediately behind it, pushing the point of origin further away. Imagine standing on a moving walkway. You aren't walking any faster yourself, but the ground is moving beneath your feet, carrying you forward. In the Alcubierre model, the entire pocket of space containing the ship is the walkway, and it is space itself that is moving, effectively surfing on a wave of distorted geometry. This is where the concept gets its potential for superluminal travel. Since the ship itself is not moving through space within its bubble, it isn't violating the rule that forbids massive objects from reaching light speed locally. It is the bubble of spacetime that is moving, and according to general relativity, there is no known upper limit on how fast spacetime itself can stretch or contract. The ship would be carried along like a surfer on a wave, potentially at speeds many times greater than that of light. A journey to a star 4 light-years away could, in theory, take mere months or weeks from the perspective of the crew, all while never locally exceeding the speed limit set by Einstein. Of course, building such an engine presents challenges that are, for now, far beyond our reach. The primary obstacle is the type of matter-energy required to create the warp bubble. Alcubierre's mathematics showed that to twist spacetime in this specific way, you would need a form of exotic matter that possesses negative energy density or negative mass. This isn't just some rare material we haven't found yet. It is a substance with truly bizarre properties that would make gravity repulsive rather than attractive. While certain quantum effects, like the Casimir effect, demonstrate that negative energy densities can exist in tiny amounts for fleeting moments, the amount required for a macroscopic warp drive is astronomical. Early calculations suggested you would need to convert the mass energy of a planet like Jupiter into this exotic form, though more recent theoretical refinements have brought that requirement down significantly to perhaps the mass of a small moon or even a spacecraft itself. The engineering of containing and shaping this exotic matter to form a stable bubble remains completely in the realm of speculation. Beyond the sheer energy requirements, there are other profound physical puzzles. Some theorists have pointed out that the warp bubble would create a horizon that would trap high-energy particles inside it. As the bubble moves, these particles would build up, and upon arriving at the destination and dropping the warp field, this accumulated energy would be released in a cataclysmic blast, vaporizing the target planet and anything in front of the ship. There are also questions about whether the crew could even influence the bubble from the inside, as they would be causally disconnected from the outside universe, unable to steer or stop the drive once it was activated. It would be the ultimate one-way ticket. Yet, despite these monumental hurdles, the Alcubierre drive remains a vital and inspiring concept in theoretical physics. It demonstrates that the laws of the universe, as we currently understand them, may not absolutely forbid faster than light travel. They may simply demand a level of ingenuity and control over the fabric of reality that we are only just beginning to conceptualize. It pushes our understanding of general relativity to its limits and forces us to confront the deepest questions about the nature of energy, gravity, and spacetime. It stands as a powerful symbol of human imagination, a mathematical daydream that proves even our most far-reaching ambitions can be grounded in the rigorous language of science, offering a distant, shimmering hope that the vast interstellar voids we see today might one day become the highways of our descendants. And so, our journey through the cosmos at its most extreme draws to a close, having traveled from the unbreakable rule of light itself to the theoretical manipulation of spacetime. We have witnessed hypervelocity stars cast out from the galactic center by the gravitational slingshot of a supermassive black hole, destined to wander the intergalactic void alone. We have marveled at pulsars, the spinning corpses of stars whose surfaces whip around at a significant fraction of light speed, acting as the universe's most precise lighthouses. We have stood in awe of relativistic jets, colossal beams of plasma erupting from active galaxies, channeling energy across millions of light years at over 99% of light speed, capable of shaping the destiny of entire galaxy clusters. And we have delved into the quantum realm, where cosmic rays and neutrinos, the universe's ghost particles, are accelerated to energies that defy comprehension in the shock waves of supernova and stellar mergers. What binds all these disparate phenomena together is more than just velocity. It is the relentless pursuit of the fundamental limits of physics. Each of these cosmic speedsters is a natural experiment, a laboratory condition that we could never hope to recreate on Earth. The furious spin of a pulsar tests the very strength of nuclear matter against centrifugal forces that would tear any other substance apart. The near-light-speed material in a quasar's jet provides a direct testbed for Einstein's theory of special relativity, with its bizarre time dilation and length contraction effects made manifest. The elusive ghost of a neutrino, changing its identity as it travels, forces us to revise the standard model of particle physics itself. By studying these fastest objects, we are not merely cataloging astronomical curiosities. We are probing the very laws that govern reality, from the infinitely small world of quantum mechanics to the infinitely large scales of general relativity and cosmology. They are our guides to the edges of known physics, pointing toward the mysteries of dark matter, dark energy, and perhaps even a deeper multi-cosmic reality. This grand tour from the quantum to the cosmic underscores a profound and humbling truth. Our universe is a place of dynamic, often violent motion. It is not a static, placid painting, but a living, breathing entity where gravity, magnetism, and nuclear forces are in a constant, dramatic struggle. The tranquility of our night sky is an illusion, a peaceful backdrop for a reality teeming with hypervelocity ejections, stellar cataclysms, and particles moving so fast they brush against the ultimate speed limit. Understanding this frenetic activity is key to understanding our own origins, for we are made of atoms forged in the hearts of exploded stars and scattered across the galaxy by these very same high-speed processes. We are quite literally children of cosmic violence and immense velocity. The exploration is far from over. With every new telescope, every more sensitive gravitational wave detector, and every ambitious space probe, we push our vision further, discovering new classes of speed demons and refining our models of the old ones. The universe continues to surprise us with its ingenuity and its raw, untamed power. So we turn the final question over to you, our fellow cosmic explorers. Which of these incredible speedsters captured your imagination the most? Was it the lonely journey of a hypervelocity star, the focused fury of a Pulsar's jet, the quantum weirdness of a neutrino, or the mind-bending potential of a warp drive? Let us know in the comments below, and don't forget to subscribe for more journeys to the edges of reality. But if the Alcubierre drive represents a distant theoretical dream, there are other concepts being actively researched today that could propel our first robotic emissaries to the stars within a human lifetime, and they rely not on fantastical negative energy, but on the gentle, persistent pressure of light itself. Imagine a spacecraft with no engines, no fuel tanks, and no roaring launch. Instead, picture a vast, incredibly thin, reflective sail, kilometers across but lighter than a paper handkerchief, unfurling in the emptiness of space. This is the solar sail, and its principle is beautifully simple. Just as the wind pushes a sailboat across the ocean, the physical pressure of photons, the very particles of light streaming from the sun, can push this gossamer sail forward. Each individual photon imparts only a minuscule nudge, but collectively, over time, this constant pressure can build up to astonishing speeds, offering a truly limitless propulsion system that requires no propellant. The true potential of this technology, however, unlocks not with sunlight but with lasers. While the sun's light is diffuse and weak over interstellar distances, we can create our own concentrated artificial sun. The concept, known as a laser sail or light sail, involves constructing a massive array of powerful lasers here in Earth's orbit, all focused into a single, coherent beam aimed directly at the sail of a distant probe. This is not a gentle push, it's a colossal shove. By directing gigawatts of laser power onto the sail for minutes or hours, we could accelerate a small, wafer-thin probe to a significant fraction of the speed of light, 20, 30, or even 50%. At such velocities, a journey to the Alpha Centauri star system, our nearest stellar neighbor at 4.3 light-years away, could be completed in just a few decades, rather than the tens of thousands of years it would take with our current chemical or even ion propulsion systems. The engineering hurdles for such a mission are, of course, monumental. The first and most obvious challenge is the sail itself. It must be nearly perfect, incredibly large to catch as much laser light as possible, yet impossibly light to maximize acceleration. It would likely be constructed from advanced materials like ultra-thin sheets of molybdenum disulfide or carbon nanotubes, and it would need to be engineered to withstand the immense laser power without tearing, melting, or being pushed off course by the slightest imbalance. Then there is the laser array, a project of staggering scale. To achieve the necessary acceleration, we would need to construct a network of lasers with a combined power output equivalent to a significant fraction of humanity's current global energy consumption, all operating in perfect synchrony across a vast area in space. The precision required to keep this laser beam focused on a sail the size of a football field as it recedes over billions of kilometers is a feat of aiming that dwarfs any technological challenge we have ever overcome. Beyond the launch, the mission profile presents a cascade of further obstacles. How would such a tiny, lightweight probe carry any meaningful scientific instruments? The answer lies in radical miniaturization, building cameras, spectrometers, and particle detectors that are no larger than a postage stamp. How would it communicate its findings back to Earth across the light years? It would need a powerful, focused laser of its own, and we would need to build vast networks of enormous radio dishes here on Earth to have any hope of detecting its faint, distant whisper. And perhaps the most dramatic challenge of all is the arrival. Traveling at even 20% of the speed of light, a collision with a dust mote or a tiny piece of interstellar debris would release an energy equivalent to a high explosive charge, vaporizing the probe instantly. Navigating this interstellar minefield would require either incredibly resilient materials or an ingenious system for detecting and evading hazards we cannot even see from Earth. Yet the profound implications of success are enough to drive this research forward. Initiatives like Breakthrough Starshot, backed by significant private funding, are actively working to turn this science fiction dream into a tangible mission plan within a generation. Success would utterly transform our place in the cosmos. For the first time, an object created by human hands would not merely drift through our solar system, but would actively voyage to another star. The data it would send back close-up images of the planets in the Alpha Centauri system, analysis of their atmospheres, measurements of the interstellar medium would be revolutionary. We could directly investigate Proxima Centauri b, a rocky, Earth-sized world in its star's habitable zone, to search for signs of oceans, continents, or even biosignatures in its atmosphere. This would not be a blurry, pixelated image from a giant telescope, but a postcard from a new world, fundamentally answering the ancient question of whether we are alone and opening a new chapter in human history, the interstellar age. The journey of this tiny, laser-pushed sail would be the first small step across a cosmic ocean, proving that the vast distances between stars are not an immutable barrier, but a challenge to be met with ingenuity.